Good morning. Welcome. For some people, I guess it's the start of their Easter holiday. Some people, I don't think so yet, but whichever one you are, it's Sunday, so it's a day off, but it's a day of hard work for us all. Welcome. My name is Nav, for those of you that haven't met me before. I teach physics at Flash Revision Lab. So today we're going to be starting the first of our boot camps this Easter. So just here, I wanted to outline what the plan is. So you've got me today doing physics paper 1. So that's the first 4 topics in the physics specification. We'll be going through that today. And then following that, we have Neen doing biology paper 1 on Tuesday. And then following that, Neen again doing chemistry paper 1 on Thursday. So that'll be the first week covered before we then get into the second week of the Easter break, looking at the paper 2, starting with biology on Tuesday the 7th, chemistry on Thursday the 9th, and then lastly, back with me on Sunday the 12th for physics paper 2. Morning, everyone. I hope you're doing well. I hope you're ready. It's going to be a hard work today. Plenty to cover. And I want to stick to as best as I can to the timings, which I'm going to show you now. So here we are. It's 10 a.m. So we're making a start. We'll make a start on our first topic. We'll then move into our break for about 15 minutes. And then a second hour before we go into lunch, about 12:15, where you have an hour, get some rest, get a bit of food, come back at about 1:15 for another hour, and another 15-minute break before we get into the last hour, looking to finish about 3:30. We'll see how I get on. Obviously, I may go a little extra in some areas, and maybe I'll finish a bit early in others, hopefully. But obviously, I'll let you know each time when our break is and how long it's for and when to rejoin. So there's no problem with that. And also, I just wanted to send this here if anyone still needs it. If they don't have the workbook printed, please do. I've sent a link here again to our page where you can sign up if you haven't and you're just joining. If you know anyone else that wants to join, just send them the link as well. They can still sign up and they will get the revision guide sent to them so they can join us wherever they are. So it's not too late still. So please do send it on to anyone you think may be interested. We're about to start in a couple of minutes. I just wanted to run through some house rules and a few things here and there in terms of quality of stream, etc. So if you want to chat here and you're not able to message, just subscribe to our channel. That will allow you to message. If you have any questions, please do send them. I'll do my best to answer them as we go through. Then as I can see, everyone's engaging in the chat, which is great. Loving to see that. Please just be respectful. And if you have any questions, make sure you ask them and I'll do my best to answer as many as I can. In terms of connection, if it goes a bit blurry, which it might do on occasion, those that have been with us on FRL classes will know. Sometimes it does get a little bit tetchy. If it does, just bear with us. The connection hopefully should come back. Or if you try and refresh the stream, it should come back to you. And if we do have an outage in the stream, just bear with me. I will send a link out to you if that does happen. Hopefully we don't have that. Also, in terms of the content, then it's going to be for higher tier. Okay, so we're going to be covering everything for foundation tier, obviously in that as well. If you want to know which bits are specifically higher tier, you can take a look at the specification and it will say HT only in it. So make sure that you look at that out for which bits are going to be specifically for higher tier only. There's a few bits of those. And then also we have some people doing combined science, some people doing triple. So I will tell the people that are doing combined science only when that ends so they can go for their break. And those of you doing triple, unfortunately, you'll be with me just a few minutes longer to cover the last bits of triple. So I'm making sure everyone is covered as best as possible. Will you be leaving it up when it's finished? Yes, the video will be available on our YouTube to have a look at. And this in terms of for exam boards, the specification I'm going through specifically here is AQA, but bear in mind that there is a lot of crossover between all the exam boards. So about 70% will be the same as well anyway, and equivalent anyway. When I get to paper 2, there'll be some exam boards where paper 1's topics are in paper 2 and vice versa. So most of the topics are a lot of crossover, so you will need it for your GCSEs. So you will get that crossover from the 2 papers if you join us for those. And yeah, IGCSE is included in that. So that's all of the exam boards. There'll be that crossover. Okay. I think that's about all I wanted to cover before I make a start. So if we're ready, we'll get into topic 1, which is on energy. So let's get into it. So firstly, we have energy stores and transfers. So we look at open and closed systems. The best way to look at this is if you think of a thermos flask, which is what I've got in this image here. If it's open, that's like saying the lid is open. Thermos flask obviously is meant to keep things warm. So if the lid is open, the heat can escape through there. Yeah, energy can be transferred in or out. Yeah, so in this case, this is where we're saying that energy and heat and matter can enter and leave the system. In this case, the system being the thermos flask. On the contrary, in a closed system, you can have where the lid is closed. Nothing can escape, right? So if you had a hot cup of tea in your thermos flask, it stays warm, right? When the lid is closed, and you can open it and drink it, it will stay warm. So when it's closed, it means heat and matter doesn't escape or enter, doesn't leave or enter the system. Okay. So that's the difference between an open and a closed system. And in those energy systems, we have a variety of different energy stores, right? So we'll go through each one here. We have thermal energy. Thermal energy is energy due to the temperature of an object. So I'm going to put this on the side here. Feel free also to annotate with me as I'm going along. I will add notes here and there. And obviously in the workbook, if you guys have gone ahead and had a look, there are different sections for with spaces to write notes yourselves. So yeah, follow along. So the first one here for thermal energy is due to temperature of an object. Then chemical energy, as I've got a symbol here, either a battery or a burger. A battery in any sort of electrical device is kind of the means by which it will work. So it's the fuel for the electrical circuit to run. Okay, equally with food in ourselves, when we eat, the food we intake, that's fuel for us to be able to use energy in what we do. Okay, so it's energy stored in fuel, or stored as fuel. So I'm just going to put here stored as fuel. Kinetic energy, I've got a car there because it's to do with motion. Yeah, so it's to do with moving objects. So kinetic energy is simply due to motion. Then the next I have here is gravitational potential. So gravitational potential is to do with the height or position of an object. So the higher up something is, the more gravitational potential energy it has. Okay, so I'm going to just say here due to position. The next one, elastic potential, as you can see, the person is holding a rubber band. So an object, when you stretch or compress it, so compress meaning squash, so like a spring, if you squash a spring, it stores elastic potential energy. So I'm going to say stretching or squashing. Then we have nuclear energy. As the image suggests, you probably would have seen it in The Simpsons if you've watched it. The power plant that Homer works at, it's like a nuclear power plant. Yeah, so nuclear power comes from radioactive substances, things like uranium. Yeah, so that's the nuclear power station there. So nuclear comes from radioactive sources. Magnetic, as the name suggests, is to do with magnets, so energy from magnetic fields. And then lastly, electrostatic forces as well, which is energy due to charges. Okay, so positive and negative charges interacting with each other. So I'll put here due to charges. Okay, so moving on, I think someone's asked, is it higher? Yes, it is higher. As I mentioned earlier, if you just missed it, higher tier is what we're covering, but obviously that includes foundation. If you want to see what's specifically higher tier, make sure you look in the specification where it says HT only in it. Okay, so we've talked about the energy types. Now I just want to get into what the different types of energy transfer are. Okay, so the first one here I have mechanically. So this is through motion, you're moving something. So say when I push a box in a room, I'm pushing it. That's a mechanical transfer of energy to the other object. Okay. The next one by heating, like a kettle, for example, that is like when you have boiling of water. So something is warming up and energy is transferring from hot to cold. So the heat in the heating element of the kettle will be used to heat up the water in the kettle. Then we have electrically. So we saw earlier with, say, a battery, or another example, any plug point in your house, and you plug in your appliance into it, then that transfers electrically to the appliance. Can you say doing work? Yes, you can, because work is done on an object. So there is a kind of interaction between those two terms. Yeah, so work done is mechanical work, we sometimes call it. So that is a mechanical transfer of energy, correct? And then lastly, I've got here by radiation. So by radiation would be the transfer of energy from the sun to the earth. It transfers heat and light via waves. Okay, so I'll put here via waves for radiation. Okay, so I've just wanted to go through here as well a couple of examples for energy transfers. Okay, so starting with when a person, here we're saying that they throw a ball upwards. Okay, so you're using the muscles in your body to throw that ball up, but you need to consider where is that energy coming from to use the muscles in your body. So in order for us to do anything or have the energy to do it, we need to consume stuff, fuel. Yeah, the fuel for us is chemical energy from food. So that's what I'm highlighting here as the input. You need chemical energy in yourself to be able to activate your muscles to move. Okay, so then because it's motion, we're transferring mechanically, because we're transferring the energy into the ball as we launch it upwards. Okay, and then that energy in the ball is now moving, so that has kinetic energy. We said energy due to movement is kinetic energy, right? So that's the energy transfer there. Okay. Then another example I've got here is for a kettle boiling water, for example. So I mentioned that is heating by energy transfer thermally. Yeah. So for example, here we have the heating element in the kettle. Okay, at the bottom of your kettle, usually when you turn the switch on in it, it heats up from the bottom. That is then transferring the heat into the water. Yeah, usually you put cold water in your kettle, so then the heating element heats up that cold water. It starts to boil, right? So you get the thermal energy from the heating element heating up the water, so the water gains thermal energy. You can rewatch this, by the way. This will be on our YouTube page at the end, so make sure you revisit our page if you need to. You can always obviously go back in this video today as well, even in the breaks, etc. So feel free to do that, no problem at all. How do you know it's higher content? Make sure you check the specification. There are specific areas that say HT only. I haven't got there yet, but as we go in later on, you will see some sections that say HT only in the specification. When we do exam questions, if we get the time, obviously there's a lot of content to go through. I have put exam questions in the workbook. So if we get to the end of the topic here before the hour or before our break, then I will try our best to try some questions as well. But it all depends on how we get through here. But we left them for you to try as well in your own time. Okay. One interesting one here is a car crashing. That's the one I wanted to mention. If we look at a car crashing, it's quite an interesting transfer because you have the car hitting into a wall, but then where does that energy go after? Because the car is moving and then suddenly it comes to a stop, right, as it hits the wall. So if it's moving, we've said the energy stored initially is kinetic energy because it's moving, energy due to movement. And then because it's in physical contact with the wall, that's where the energy is being transferred to. So anytime there's physical contact, we talk about a mechanical transfer of energy. Okay, so it goes from the car and into the wall. The wall may not necessarily move, right? It will stay in place, and the car is the one that crumples or breaks essentially. So where is that energy going? It can be one of a few things. It could be obviously you hear sound in the crash, and then the main one which I've highlighted here is that it can be thermal energy. Okay, so energy transferred to the surroundings. In this case, the surroundings is the wall. The car will transfer thermally into the wall, and the wall will feel a lot hotter once the incident takes place. So one I wanted to put in here is one for a falling object. Okay, so in terms of the input energy, this is, for example, let's take the first one I gave was a ball being thrown in the air. Here I'm holding the ball and I'm going to let go of it and it's going to fall to the ground. Okay, so when I'm holding it in this position, it's an energy due to its position, right? It's higher up than where it's going to end up. So it's energy based on the height of the object. This is gravitational potential energy. Okay, so I'm going to say gravitational potential energy, or just gravitational, is our initial store, okay, where the ball is holding its energy to start with. So I'm going to say ball in the air. And then what is it going to turn into? So as I drop the ball, the gravitational potential energy is going to decrease because its height is decreasing, but the ball is moving and it's going to move faster. So energy due to movement, that means our output is kinetic energy. So I'll put here kinetic due to ball falling. Yeah, so that motion leads to a kinetic energy being built up in the ball. Correct. And then lastly, I want to identify what transfer that is. And now because that is a motion, there is a transfer from staying still and then falling through the air. This is an example of motion, so it's a mechanical transfer. Okay, so I'm going to put mechanical or mechanically as the type of transfer of energy here. Okay, that's an example I wanted to give. So a few things there on energy transfer and the different types of energy. They do sometimes give you questions in exams talking about input and output, and they might leave a blank for you to fill in as a type of example, and also things on the types of energy transfers as well. So the different types of energy. Yes, great. Mechanically, people have got it. Excellent. That's good to see. So people have got some stuff that they've learned so far, which is good to see. That you guys know it already. It's a good place to be in as we get into start of really revising for exams. So use this as a point to test yourself as well, which is great. Good to see that in the chat. Okay, so here I've put at the end each section the topic list from the specification, so you can see what's being covered and you can see how that's compared to what we've done just now. So feel free to have a look, and you can obviously tick through here depending on your knowledge. If you understand it or you don't, you can leave it blank. So just a good way to track it as you're revising. So make sure that you go back through this revision guide and use it to your advantage to make sure you know what you've covered. Okay, so physics always has calculations in it, okay? And these are the first that we're going to see. So several equations in exams this especially this year, I think they don't give you questions that contain the equation in the question. So they'll say to refer to the equation sheet. You will get the formula sheet which contains the equations, but it won't be in the questions anymore. So these, you don't necessarily need to remember them, all of them. So don't worry about remembering every single one, but it's about applying them. That's the important thing. Do I have to know the definition of like all the energy stores or not? Yes, you do, which is why we went through them. Obviously, if I go up, I can show you briefly. We have put all the definitions in the revision guide as well. As you can see, they are all here. So make sure you refer to these as well. But yes, you will need to know them because sometimes they'll ask you straight out what the definition is, or they'll ask you to fill in the blank for types of energy transfer. So again, testing that you know what all of them are. Okay, so the first equation here we have is for kinetic energy. Okay, kinetic energy equaling half times mass times velocity squared. So as we said, it's energy due to the movement of an object. So movement is dictated by speed or velocity, how fast it's going. So we need to know the mass of it and also how fast it's moving, half mv squared. And here we've got an example of a question with it, which I'll come back to later on because I want to give an example of a slightly more difficult one that's in the revision guide a little bit later. So we'll look at that shortly. The next one, elastic potential energy. Quite similar in its structure to kinetic energy. You can see half times m times v squared, but in this case for elastic potential, it's half times k times e squared, okay, where k is a spring constant, essentially a measure of the stiffness of the material, right? The greater the spring constant, the stiffer it is, the harder it is to stretch, okay? And then the e stands for the extension. The extension is how far it stretches beyond its original length. You think of a rubber band, and when you stretch it, the difference between when you started and where you're holding it to, that's the extension. Okay. So extension is a length, that's in meters. Any type of energy we measure in joules, and then spring constant is newtons per meter because it's the amount of force we need to stretch an object at 1 meter, for example. Okay, so the spring constant is in newtons per meter. So in calculations, I've stressed this to the guys that have been in FRL classes. Every time you do an equation, make sure you have everything in the correct units. Okay, and again, it's something we'll check for when we do an example in just a minute. So that's two of the energy equations. There's one more, which is for gravitational potential energy. Now, we said earlier, for example, in the image of the plane or in my example of the falling object, it's due to the height or position of an object. Okay, so the higher an object is, the more gravitational potential energy it will have. So therefore, the equation also has height in it. Okay, and the equation for it is mass times gravitational field strength times height, or mgh. Okay, where h is a height, it's a distance, so it's measured in meters. Mass is in kilograms, and gravitational field strength is in newtons per kilogram. Okay, so there is a standard value for gravitational field strength on Earth, which is 9.8, but that is just for Earth. Yeah, so I'm going to put here on Earth. Sometimes if it's not on Earth, they will mention that and give you a different value for the gravitational field strength. Okay, but for Earth, the standard value is 9.8. So that is the three different equations that you have, but sometimes there'll be a question where it kind of involves more than one equation. Okay, and we're going to look at that just shortly. So I'll get into that on the next page. I think it's this one. Yeah, this is the question here I wanted to check. Okay, because sometimes they'll combine more than one equation in a question, and it can be slightly more tricky. So let's take a look. It says a ball with a mass of 1.2 kilograms falls off a building that is 23 meters tall. How much gravitational potential energy does it have before it falls? So looking at a question like this, I will always underline the pieces of information that I think are important. So things such as the mass, 1.2 kilograms, and they've told us the building's height, which is 23 meters. So that's the height. And it's asked us to calculate gravitational potential energy. Okay, so here I've put down what do we know and what we don't know. EP for gravitational potential energy. We don't know it. We're trying to find it out. The mass they've given us, 1.2 kilograms, and then the height of 23 meters. And this is a building, so it's on Earth. So the standard value we're referring to for gravity or gravitational field strength is 9.8. Then we have a look. Do we have everything in its standard units? Mass in kilograms, that's correct. Height in meters, that's also correct. and then gravitational field strength in newtons per kilogram. So that's fine. Everything is in its standard units. So we simply substitute in the numbers we have. So that's m times g times h, and that gives us a value of 270.48 joules. Okay, so here, obviously, you'd use a calculator for that. That will give you your answer there. So that's part A of the question. Now, part B is saying, what is the speed of the ball as it reaches the ground, just before it hits the ground? Okay, so what we need to envisage here, and I'll draw it on here, you're dropping the object, the ball, from the top of the building, and it's going to fall down. So similar to the example I gave before, what is the energy transfer? It starts from gravitational potential energy, and then it falls down. So it's moving. So that GP that it's losing because its height is decreasing is turning into kinetic energy because it's speeding up. Remember that mechanical transfer. So we're saying that all the kinetic gravitational potential energy is losing is turning into kinetic energy. Okay, so I'm going to put here GPE loss equals KE gain. Okay, so then that means that the amount that we said is started with, the gravitational potential energy, which is the 270.48, all of that is turning into kinetic energy. Okay, so we're going to say the kinetic energy is now 270.48. The mass of the ball doesn't change. Yeah, it's still 1.2 kilograms. And they've asked us to calculate the speed. Yeah, that's what they want us to find, the speed of the ball. So we then go to the equation sheet, or if you remember it already, you can remember what the equation is. In this case, I've shown you here, so I've put it on the side, half mv squared. That is the equation we're going to be using. So we need to find the velocity. Okay, everything is in its standard units, so we can look at the equation. Ek equals half mv squared. You can either choose to substitute the numbers in and then rearrange, or rearrange the equation first. Here, I'm showing what the equation would rearrange to first. Okay, reason being is you would take the half m and you'll move it to the other side so that E is on its own. To do that, you divide both sides by half m. That's why it ends up on the bottom. And that gives us v squared, but then we want v. So to get from v squared to v, you have to square root. What you do on the left, you do on the right. So that is where this square root comes from. Okay, so it's the square root of the kinetic energy divided by half times the mass. Knowing that, we now substitute the numbers in, 270.48 for our kinetic energy, and then at the bottom, half times the 1.2. Okay, put that in your calculator, is root 450.58. Put that in your calculator, you get to 21.23. Okay, one thing to note, okay, I'm going to put it at the bottom. When it comes to questions, sometimes they will ask you to give your answer to a certain number of significant figures on occasion. Okay, if they do, make sure you pay attention to that. So here, if it said 2 decimal places, we're absolutely fine. We've given it to 2 decimal places. Yeah, don't give an answer that has so many decimal places on the end. They don't really want to see that. Yeah, so 2 or 3 significant figures. Yeah, those are the best 2 figures I'd say to use, unless they tell you specifically in the question. Are there any ways to memorize mnemonics for these topics and memory tricks? So we do have some coming up, Coral. They will be in here later on. In this topic, it's more equation based, and then the energy types. Feel free to drop any in the chat. If anyone has any, do feel free to share. We may make videos out of it as well, and we'll give you a shout out. So let us know if you have any. We'd love to know. But there are some that are coming up. So especially in the next topic, there are quite a few. So we'll have some that we'll put in there to help. But if you know any, then yeah, feel free to let us know. Okay, so that is the examples of energy calculations. So we're going to move on from here. As you can see in the spec, I'll just quickly cover it. See, there's a section on kinetic energy and its equation, elastic potential energy and its equation, and then gravitational potential as well. Okay, so that's that section covered. So the next thing, energy changes in systems. Okay, so here we're talking about specific heat capacity. A question that comes up a lot when it comes to specific heat capacity is the definition for it. Okay, and the key thing, we have put it here, and I'm going to underline the key sections of it. You know what? I might highlight it instead. Let's highlight it. So the key bits are the energy. It's the energy required, first of all. Okay, it's measuring how much energy is needed. So how much energy is needed to raise the temperature of 1 kilogram of a substance by 1 degree C. Okay, so to raise 1 kilogram of a substance by 1 degree Celsius. That's the definition. Okay, it comes up a lot, so it's important that you do remember that definition. Okay, so the energy required to heat up 1 kilogram of a substance by 1 degree Celsius. Now, Depending on the value of specific heat capacity of a substance, it tells you how easy it is to heat up or cool down. So comparing these numbers, 4186 for water compared to 1670 for oil, it means that oil is easier to heat up. Less energy is required to raise its temperature by 1 degree C. So it's easier to heat up and cool down. Okay, that's the comparison we've said. So here I've put it as well, that the, sorry, get my highlighter. Oil has a lower specific heat capacity, and so it needs less energy to heat up. Yeah, so oil needs less energy to heat up because the specific heat capacity is less. Okay, so the higher the specific heat capacity, the harder it is to heat up. Okay, again, there is another equation. We've seen a unit here for specific heat capacity, so there will be an equation linked to it as well. Okay, that equation is change in thermal energy. So delta E, when you see a triangle, that means change in. Okay, so you always need to note this triangle means change in. So change in energy, or thermal energy in this case, is M, which we've seen already, is mass, times C, the specific heat capacity, multiplied by, again, we see another triangle, a change in, but this time the Greek letter theta for temperature. Okay, so MC delta theta, mass times specific heat capacity times the change in temperature. And that gives you the change in thermal energy that you need to heat up or cool down a substance. Okay, so when you rearrange that, it gives you the units for specific heat capacity, which you can see here are in joules per kilogram degree Celsius. Okay, so that is usually the standard unit for that. Joules being energy, and then over, so slash meaning over kilogram degree Celsius, so mass times the change in temperature. Okay, that comes from this equation here. So if I want to find the specific heat capacity, I want C on its own, don't I, in this equation, which means the mass and the change in temperature need to move to the left-hand side of the equation, meaning you divide everything by M and delta theta. That's where this comes from, M delta theta. So if you look at all their units, like we said, energy in joules, mass in kilograms, and change in temperature in degrees Celsius. So you put those units together, it's exactly what it says here, joules per kilogram degree C. That's where it comes from. Just having a look in the chat, if there's any questions. Okay, people are talking about chemistry, that will be later on. Does efficiency cross over this topic? A little bit. It does a little bit. GCSE study account, a little bit. We will see it in energy, and efficiency does come up. So there is a crossover, you're right, when it comes to transfers. Do you get the full equation sheet? You should get a full equation sheet. And that's why they're asking you in the question, use the equation sheet when you're calculating, doing a calculation question in the exam. Cool. So moving on from there, I'll look at the required practical, the first one. Okay, the first one in physics that we're seeing, a dreaded 6 marker if you see it in your exam, but the point is we don't want you to dread it. Okay, the key thing I want you to take away before I go back to this to show you how it works, I want to cover what the important thing is when you do experiment 6 marker questions. Okay, when you think about it, a 6 marker is like 3 2 markers. Yeah, I try and make it simpler in my mind. I go, okay, if I break it down into 3 sections of 2 marks are easier to get. Yeah, you can quickly gather those up and you'll get 6 marks. So the first thing you want to put here in an experiment, when they're asking you to explain how it works or what you do in the experiment, the first thing you need to make sure is you identify your apparatus. Okay, so that's the first point here. Number 1, identify your apparatus. Not apparatus, if I can spell, apparatus. Cool. So that is knowing what instruments you're using to measure with, what you're holding things in. Say if you're using water, what you're holding the water in, or what object you're measuring, making sure you're clear with all the pieces of equipment you're using. Okay, so that's identifying your apparatus. The next thing, we're trying to collect data, aren't we? So like I said, what are you measuring? You need to state the values that you're recording with those pieces of equipment. Yeah, so if you're using a ruler, you're going to say measure the distance. If you're using a thermometer, say measure the temperature. Okay, so those are the kind of things you need to make sure you're covering what each of those pieces of equipment is measuring. Okay, so I'm going to say here, state the values being recorded. So in other words, that's your method, isn't it? How you're carrying out the experiment, what are you measuring? Okay, so now you've done that, you've collected the data. The last bit is now interpreting your results. How are you going to use that data to give you an outcome to the experiment. Okay, so here I will say interpret results. The reason I say that is because sometimes it may be you use that information to plot a graph to find some sort of trend in the data. Yeah, so it could be plotting a graph. But sometimes if you're looking for a value of something and then you're going to compare those values later, you do a calculation. Yeah, so you use your data to calculate something. So I'll say or calculation. Yeah, that's two ways of trying to interpret the results that you've got or the data that you've got. Are we going through all the required practicals? Yes, Sammy, we are. We will be. Yeah, everything you did exactly as we always preach. It's everything you need to know for your exam. So every single required practical throughout physics we'll be covering. Obviously, not all today. There'll be some in paper 2, but everything in paper 1 will be covered today. Do we also identify variables? So when it comes to giving your marks in this question, you don't necessarily need to say which one is which variable, but in terms of what you're measuring, you allude to that in a way. Yeah. So when I'm going to go up now and go through this experiment for specific heat capacity, you kind of allude to what you're using as your independent and dependent variable, which is what I'm guessing you're referring to. Yeah. So in this question, you don't, they said explain or describe an experiment you would use to get results, you don't need to specifically state it, but you can. Obviously, any information you show can help, but really identifying the apparatus, stating your measurements that you're making, and then interpreting your results are the way you're going to get the marks. So apparatus is just another word for equipment. Yeah. So when I say apparatus, taking a look at this, see I've put here equipment needed. Yeah, so I'll underline that. That is your apparatus. Yeah, so I'll put that here. Sorry, I'm so used to mentioning the word apparatus as like when we were doing it in school. I'm just used to using that word. But yeah, it's the equipment that you need. Okay. So in this case, we're looking at how to measure the specific heat capacity of a solid. Okay. So in this case, we're going to take a metal block, aluminium. Okay. So this is the part that we're measuring. So we need a metal block because that's what we're going to measure. Yeah. And then we're going to calculate a specific heat capacity. So what information do we need? We need to know, if you think about the equation, E equals mc delta theta. So to find C, our specific heat capacity, we need energy, a way of measuring the energy used to heat it up. We need to look at the temperature change, delta theta. So we need something to measure the temperature. And then we also need something to measure the mass of the object that we're investigating. Okay. So the metal block is our object we're investigating. To measure the mass, M, we've got the mass balance. To measure the temperature, we need a thermometer. And then to measure the energy, I've got here a joule meter. Remember, energy is measured in joules. So a joule meter is something that measures joules, measures energy, essentially. Okay. So that is what the joule meter is for. So here we've listed out the equipment. You don't need to list it out exactly like that in the exam. I would say make sure you're covering that in your mind. Okay. So have I got all the equipment I need? Sometimes they leave you a space in the question. There'll be a blank and then some lines for text underneath. If you want to draw a diagram, then you can introduce some of the equipment and show drawings of it if you wanted. So let's say they would ask you a question on practical statement, then you have to identify it. Yeah. So sometimes they'll say they'll have an experiment and then they'll ask you what is the dependent and independent variable. Correct. That's where you tend to see them asking for that. Will they show us an image of the apparatus? Sometimes they do, sometimes they don't. Yeah, so that's what I was just saying. There is a blank sometimes they'll leave to say you may use a diagram in your answer. Okay, and in that case, you could use it. You don't have to, but you can use it to aid yourself to get some more marks. If you're struggling explaining stuff, draw it in a diagram to show the equipment, basically. Okay, so remember, this is specific heat capacity. We're trying to see how easy or difficult it is to heat something up. So in this case, we need to heat up this metal block, right? That's the aim, so that we can see how much energy is needed to heat it and therefore its specific heat capacity. So we need an immersion heater. Okay, an immersion heater is only going to get its heat when you turn it on. Okay, so it has something to turn it on, which is a battery pack. So that's what's giving it energy to turn it on. That turns on, heats up the metal block, and we look at the temperature change in the metal block. Okay. The important thing I've added here is insulation. Okay, and we're going to come on to that later on because we want to make sure our experiment is as accurate as possible, and that's what that's for. Okay, so we've mentioned all the apparatus, and now we're going to talk through the method, the procedure. What are we going to do to record the values we need? Remember, we need energy, we need mass, and we need change in temperature. Okay, so the first step, like we said, we measure the mass using the mass balance. Okay, so that's your first step. So we know the mass of the block. Okay, so I'm going to put the equation on the side here. Delta E equals mc delta theta. Now I'm just going to color coordinate the points here. So measuring, using the mass balance to find the mass, that ticks this off. We know the mass now, okay? Then you can see we're talking through setting up the experiment. So as I said, we need something to heat up the block. That's the immersion heater here. So the immersion heater is put into a slot in the block, and that's connected to the battery pack. So it turns on. It starts to heat up the metal block. Yeah. So as soon as we turn it on, we want to measure the temperature of the block before we start heating it. Okay. So then we can work out after a certain amount of time, say 5 minutes, what does the temperature rise to? Then with those two values, we get a change in energy, don't we? Yeah, change in temperature, sorry. From the beginning to the end, the final minus the initial temperature gives us a change in temperature. Okay. So you don't have to add a couple of drops of water into the metal block because you've got the immersion heater. So that's going to do the job. So no water required in this experiment. Independent variable is what you change in the experiment. Dependent is what you measure. Correct. Exactly. Good. Okay. So we heat up the block. We then measure the energy using a joule meter. Yeah. So the energy used by the heater is connected to a joule meter, and you can read the recording of the joule meter for the amount of energy used. Okay. So turn on the immersion heater and start heating the block. Record the initial temperature. Okay, so I'm going to do this in blue. Record the initial temperature of the thermometer. And then once you have finished, turn off the heater and record the final temperature. Yeah? That initial minus final gives you your change in temperature. So that's the blue bit covered. Okay. We then also record the energy reading on the joule meter. Yeah, so remember the joule meter, it needs an initial measurement from when we start the experiment, and then we need an energy reading once we've finished heating it. Okay, so let's say we started, and then 5 minutes later we measure it again. So then again, before, energy initially and energy at the end, you find the difference, and we get the change in energy. That covers this section. Okay, so delta E. So you can see we've ticked everything. The only thing we don't have is our specific heat capacity, C, and that's what we're trying to find, aren't we? That's what we're aiming to do with this experiment. We're trying to find it. Okay, so we've explained all our equipment. We've then talked through the procedure of how we're going to record the information we need. Then it says use the specific heat capacity equation to calculate the specific heat capacity. Yeah, remember calculating, I said about interpreting results. In this case, this is your interpretation of results. You need to calculate it to work out the specific heat capacity, and then you get your answer. Okay, so if I walk through that one more time, first thing, measure the mass of the object, in this case, the metal block. Okay, measure its mass. Then, before we start heating, measure the temperature of and the joule meter reading before you start heating. Okay, so the joule meter connected to the immersion heater, measure that reading as soon as we turn it on. Then we measure the initial temperature as well. What temperature is the block starting at? Then wait 5 minutes or 10 minutes, and then we record the final reading on the joule meter and the final reading on the thermometer. So from there, we can do initial minus final temperature for the change in temperature. So I'll do that in blue because that's what we're doing here. So final minus initial temperature gives us this. And for the energy, remember we have the joule meter. So we read it at the beginning and we read it when we finished heating. So final minus initial joule meter reading. And that is what gives you the change in energy. And then the last step, we use the equation to calculate the change in the specific heat capacity, sorry. Okay, so those are your different steps. They may tell you to draw a diagram. It's not a must. They won't say you have to draw a diagram. They will ask you to explain the experiment and then sometimes say you may draw a diagram to help your answer. Okay. So in this here, you can take a look at this later, but just to show you, this is just basically some of the information recorded. So you can see a mass, a temperature at the end, an initial temperature and a final temperature. So you can see with those two, they've then found the difference, 57 minus 25, giving us a value of 32. So that's our delta theta, our change in temperature. They then took the joule meter reading as 37,315. So we have energy, we have mass, and we have the change in temperature. All three things here, everything in its standard units. So all we need to do is use the equation for specific heat capacity and substitute our numbers in, and we get a value. So that will be at the end of that experiment. The initial meeting would be 0 though, exactly. You do have to check, okay? You tell them you take the initial reading, and that's why here, for example, the joule meter reading was 37315. There is no showing of initial reading because usually it'll be 0. You haven't applied any energy to it yet. Correct, yeah? Sometimes on your environment, though, it may be warmer, so there may be some sort of energy coming from it. But usually, if you're just starting, it should be 0. Frozen, no problem. Looking forward to seeing you joining in a bit. And obviously, remember, you can watch this back, so no problem at all. Okay. So this bit is for, this is a little bit extra regarding heating a liquid. So we've done it for a metal block, right? But we haven't done it for a liquid. So the only difference here is you've got the immersion heater, in the same setup we did before, but this time it's in a liquid instead of a solid. We have the joule meter, we have the battery pack. The difference is we're not measuring a metal block, right? So we have to keep the liquid contained somehow. So we use a polystyrene cup and a lid, okay? The reason it's polystyrene and the reason we have a lid, if you think about the very first thing I said about closed systems and open systems, the thermos flask. If you keep it closed, energy is not going to escape, right? So we don't want to heat up the water in the cup and then it then escape and go to the surroundings. It's then going to take longer to heat the water. It's not an accurate experiment. You don't get a reliable result. So that's why we put insulation on it. In the same way, sorry, I missed it before. I did mention I was going to say it. Insulation here goes around the metal block to cover it. Again, so the heat from the metal block doesn't go to the surroundings and all the heat remains within it. So then we're measuring exactly what is needed to heat the metal block and not anything else. Okay. In that same way, we do the same for the cup and the lid on the water to make sure all the energy we're using is to heat the water only. And as we've said here, it makes the measurements more accurate. So I'm just going to highlight here. It makes it more accurate. Cool. Okay, hope it's going okay so far. Obviously, I have to kind of pace through this to make sure we get there and get through everything in time. So hopefully that's okay. I'm doing my best to answer your questions. Let's see, what is there? Will we do a convection and conduction? Can we look at different types of errors? I'll try and get to errors. It's kind of spread throughout physics. I'll see if I get a bit of time a bit later on. I'll bear that in mind, and we'll try and get into errors a bit. And then we do conduction and convection. It's kind of involved in heat transfers, but they don't mention it too much. We've got it a bit later on here in terms of heating home and insulating the home. So we'll come on to that in a little bit. Okay, so here, this is a bit on power, our next equation, okay, for energy transfer. So here we have power is basically the rate of energy transfer, okay? So how much energy is transferred over a particular time. When we say rate, it's something over time. So it's the amount of energy transfer over time. Okay, the 6 points for the 6 marker, I've gone through them. Be free to go back to it. I'm just conscious of the time. I'll try and come back to it at the end later on, but it's all broken down just before. Okay, so all those different points, 2 marks you get for the apparatus, 2 marks for the experiment, and 2 marks for getting the and then a calculation for the specific heat capacity. Okay, so that's how you're going to get your marks for that experiment. Okay, so energy transferred over time, or the rate of energy transfer, is equal to power, giving us the equation power equals energy divided by time. Okay, what I've put here is that also you might see that instead of energy transferred, we say work done. Those two terms are interchangeable. Okay, so work done is the rate of it is the same as energy transferred. So I'm just going to put that here. Work done equals energy transferred. Yeah, they are used interchangeably here. The standard unit for power is watts. Okay, if you think of energy, we know energy is measured in joules, as we discussed earlier. The standard unit for time is seconds. So you could say energy divided by time, joules divided by seconds, joules per second. That is also correct. But the standard unit for power, otherwise, we call it watts. Okay, because I think the guy that came up with it, his name is Watt. So he's put his name in history by making himself the unit for power, watts. Okay, so 1 watt, as I've put here, I'll highlight this as well. 1 watt is 1 joule per second. It's the same thing. Okay. So here we're looking at applying it and how power compares. So if something has more power, we say something more powerful. Usually we think of someone being more powerful than someone else is like stronger. Okay. But power is all about how quickly energy is transferred. Yeah. So if you transfer the same energy over a shorter time, then you're more powerful. You're doing it quicker, basically, aren't you? Yeah. So in this case, we're comparing the power of 2 different motors. Okay. One motor being 8 watts and the other being 2 watts. So the numbers indicate to you, 2 watts is smaller than 8, so the power is lower. Okay, how does that affect the way it lifts the mass? It's the same mass we're talking about. They're both 1 kilogram, and we're talking about the same height by 1 meter. Okay, so let's take a look. Energy transferred, we're trying to lift it by 1 meter. Okay, so it's gaining gravitational potential energy, isn't it, from what we spoke about earlier? So I've introduced the equation here. GPE is mgh. Yeah, so mass times gravity times height, which is a mass of 1 times 9.8 for gravity times by the height of 1 meter. So 9.8 joules is the energy being transferred. However, the time taken to transfer that energy depends on the power of the motor. Okay, so if we compare the two, the energy transferred by the 8-watt motor, the power, sorry, of the 8-watt motor is 8 watts, and the energy transferred is 9.8. So you do 9.8 divided by 8, giving us a time of 1.2 seconds to lift the mass. Okay, whereas the 2-watt motor will be the same, but it's 2 watts instead of 8. So we do 9.8 divided by 2, which is 4.9 seconds. So can you see here, the more powerful motor transfers the energy in a shorter amount of time. It does it faster. Okay, and this is the point that I'm underlining here. The 8-watt motor lifts the mass even faster than the 2-watt motor. Okay. Do you have homework like normal FRL classes? No, obviously this is for your revision, right? So I'm trying to go through all the content. At the end of this revision guide, you can see there are questions for you to try. So please do take a look and use it for your revision. Yes, it's questions that we've obviously, one or two may have done before, one or two you may have seen before, but there are different ones also. So there's a big variety of questions on the topic, essentially. Yeah, just to test yourself, but no homework as such. Okay, that's the topic of power. So moving on, we're looking at energy transfers in a system. Okay, and by this, we're talking about how energy is transferred and where we get losses in that transfer of energy. Okay, so here we can say, for example, the example I've chosen is a mobile phone. Okay, and the aim of a mobile phone, when it vibrates, to give you a notification, right? So that's one such use. Okay, the other such uses can be, obviously you want to see the screen. So there's light energy being given off, and then sound energy if you're playing a video or watching something. Yeah, so those are your useful energy transfers. Where does that all come from? The phone is powered by a battery, isn't it? There's a battery in your phone, which obviously you plug into charge. That is your store of energy from your battery. A battery stores chemical energy. So that is the store here. We then have a final store being the kinetic energy of the motor, causing the phone to vibrate. Yeah, this is the application I'm looking at. How does it do that? It's through the circuit in the phone. It transfers electrically in this case, okay, because the battery transfers the energy through the circuit to cause the phone to vibrate. So it's an electrical transfer. Okay. However, that isn't the only transfer that happens. Yeah? In reality, if your phone key is vibrating, if you're using it a lot, what happens? It gets hot. Yeah, your battery warms up. So there is a type of energy transfer where the chemical energy from the battery transfers electrically to thermal energy in the phone. It's not what we want. It's the undesired option, but it does happen. Okay, and this type of thing where you get this energy essentially wasted into a form that you don't want, a less useful form, we say that the energy is dissipated. Okay, dissipated being a scientific term for waste, essentially. Okay, so wasted energy. Okay, so the aim, obviously, in everything, and someone mentioned this earlier, now we've come to it, is how you make things more efficient. Yeah, and that is by reducing unwanted energy transfers. Okay, so we're trying to make things more and more efficient. So here, someone also mentioned about conduction and convection. We briefly cover it in a way here when we talk about thermal conductivity. Yeah, the prime example in your house, you want to keep your house warm, otherwise you'll be cold inside. So how do you prevent heat from escaping and keeping the heat that you're using from, say, your radiators, etc., in your house? Okay, there are several methods for that. One type of thing is loft insulation. Okay, others being draft excluders around your doors, double glazed windows. All those are options. Cavity walls. Yeah, those are all your different options. And what they do is reduce what we call the thermal conductivity. Okay, the thermal conductivity is how well something conducts heat. Okay, so I'm just going to highlight that here. How well a material conducts heat. If it's a high thermal conductivity, it conducts a lot. So someone mentioned conducting, it allows heat to pass through it. Okay, so the higher its conductivity, the more heat passes through. That is not what we want when we want to keep things warm. Yeah, we want a low thermal conductivity, meaning it's a good insulator. Okay, so that's the key aim here. So you can see, as I've mentioned underneath, it reduces energy transfer by conduction. That is what these things like loft insulation and draft excluders will do. It prevents heat transfer by conduction because it absorbs. It's a good insulator, keeps heat in. Okay. This stuff confuses you a lot. This is the thing that I understand people do find it a bit difficult, because conductivity is a measure of how things conduct, how it transfers heat. Yeah? You want to avoid doing that. So when you're trying to keep your house warm, you want things with a low conductivity, good insulation. Okay, that's the way they work, the opposite of that. So each of these, you can see we've spoken through. You can take a look, the different types of heat transfer it prevents. Okay, so loft insulation, it's like a woolly material. Yeah, so woolly things keep you warm. That's a good insulator. It also has pockets of air in it. Okay, so if the heat is trying to transfer by air, the air is trapped in that woolly material. The air can't move. So if the air can't move, you don't get heat transfer by what we call convection, heat transfer through liquids and gases. So loft insulation is an example that prevents both conduction and convection. Okay, so it has a very low thermal conductivity and it's a good insulator. Okay, so I'm going to say here, just to refer to low thermal conductivity. So therefore, it's a good insulator. Okay, so that's an example. There are different ones. So conduction and convection, the difference is conduction is heat transfer through solids. Convection is heat transfer through liquids and gases, what we call fluids. That's the difference. Another way to reduce energy losses, okay, is reducing the heat transfer by friction. Remember, if you rub things together, say even my hands are pretty cold at the moment. If I want to warm them up, I'll rub them together, right? That's friction between them, generating a transfer of heat energy. You don't want that when you're doing stuff like here, riding a bicycle. Yeah, sometimes the chains can get a bit hard to cycle with. So what they do is you lubricate the chain. Yeah, so the chain, when you touch, is a bit greasy. Yeah, because there is some oil or grease put on it, so it can roll over the chains easier, and it makes it easier for you to ride your bike. You're reducing that heat energy transfer through friction. Okay, so that's energy transfers. Then we'll talk about the equation for efficiency. Again, someone mentioned it in the chat earlier. Efficiency is how well it transfers energy from the input to the useful output. So when we say for the phone, the more efficient the phone is, the less energy is turned into heat energy. Remember we said the phone can warm up? The less the phone warms up, the more efficient the transfer of energy is, because it's being used for what we want it to be used for, instead of wasting or dissipating that energy. Okay, so here you can see an example of the equation. So it's useful power output or useful energy output over total energy input. Okay, so in this question, it says a laptop uses 1.2 kilojoules of chemical energy from its battery, but 800 is dissipated as heat. Yeah, so that's wasted energy. So they're asking, what is the efficiency? So if we need to use the equation for efficiency, we need the useful output first. Okay, they've given us the dissipated, the wasted output. So the useful output is the rest of it, isn't it? If whatever's wasted, the remainder is useful. So they've told us the input is 1,200 joules, right? 1.2 kilojoules is not the standard unit. Joules is. So to convert from joules to kilojoules, we multiply by 1,000. So that gives us 1,200 joules. The 800, which of that is wasted or dissipated. So to find the useful output, we just take away the 2, giving us 400 joules of useful energy. So therefore, using the equation, we just put that useful output at the top, 400, divided by the total input, which they said is the 1,200 from the battery, giving us an efficiency of 0.333. Someone mentioned that there, can it be a percentage? Yes, you can. You can multiply by 100 and give you a percentage. Either way is fine. Yes, you can give 0.33 or 33%. Either one will give you the correct answer. And as you can see, I've literally mentioned it underneath here. You can convert the efficiency into percentages, and that will be allowed as well. So as we said, if you want to reduce energy wasted and improve the efficiency, you want to reduce friction, air resistance being another one. So if you reduce air resistance, you get less resistance to your motion. There is a cleaner or more efficient energy transfer. In circuits, you reduce the resistance. So the less resistance there is, the easier current will flow. And then reducing sound, for example, that would be another way to reduce the energy transfer. The timing is our UK time, that's correct. Okay, covered efficiency. This is the triple only section. I will come on to that at the end, so we'll move on from there. The next chunk of this is energy resources. Okay, so here in these type of questions, we compare non-renewable and renewable resources, and also how good they are in terms of using them as an energy resource for energy supply. Okay, so non-renewable, as the name suggests, you can't renew it. It doesn't come back. It's not reusable. Okay, so once you use it, it's gone forever. Okay, so those type of things here we can see in the table: coal, oil, and gas, what we call the fossil fuels, and then nuclear power. All of those, you have an energy resource that once you've used it, it's gone. Okay, renewable are all types of resources that keep coming back. You never run out of them. They're always available. Okay, so they never run out. So then here we have examples: solar energy, wind, water waves, you always water waves in the sea, hydroelectric, so this is from falling water, so things like when you place a water wheel under a waterfall and you use that energy to create a motion. Yeah. Tides, so the rising and lowering of tides, you use that to harness energy. Biofuel, things such as plants and wood, you use that as fuel. And then geothermal is an example I'll go into a bit more later on as well. They're all types of renewable energy, okay, things that are always available and never run out. So what I want to get into here is the advantages and disadvantages of these different types of energy resources. Okay, a question again that can come up as like a 6 marker comparing different types of energy resources and which ones are better and why. Okay, so they may ask you what are the good and bad things about each. So I'll go through an example of these later, but I want to mention firstly the key points of each. Okay, so what are the key factors when you compare these different energy resources? So the first thing you want to compare is the energy output between them. Okay, which has a better energy output? So again, I'm going to compare it as we go through the examples. I'm going to pick one renewable and one non-renewable to compare. And you can see as you go through the tables in the revision guide how they compare and the similar themes, this being one of them. Okay, so a good energy output is what we want. The more then we can provide for energy in the whole country, for example, right? We need a lot of energy. We need something that has a high energy output. Then the next thing we can compare is their reliability. Okay, so how often we can expect a constant output. Yeah, some may give you a high output, but they may not give it all the time. Okay, things such as wind power, solar power. The sun isn't always out. Even today, it's a bit grey. You're not going to get as much solar energy as if it was a clear blue sky and the sun is beating down on us. Yeah, so you get less energy transfer then, but you'll get more energy when the sun is clear, when the sky is clear. Sorry. So reliability can play a factor. The other thing, an important factor, money, the cost. Yeah, how much does it cost to run? How much does it cost to build or install? If you're thinking like solar panels, they're quite expensive to fit on your house. Yeah, is it worth it for the amount of energy it gives you? Depends where you are. If you're in a country that's always hot, always sunny, yes. Yeah, if it's somewhere like here, maybe not so much, but it's good in the summer, not so good in the winter. Hi Ashton, good to see you. Anyone know how to remember the difference between wave energy, tidal energy, and hydroelectric? So hydroelectric is to do with falling water. Yeah, all in the names, right? Waves is to do with the passing waves in the ocean, and tides is to do with pulling the water based on the moon, right? The moon has a gravitational pull; it pulls the water up in high tide, and when it's further away, it's low in low tide. And all of them use a motor to generate electricity energy from that. Okay. Okay, so 3 of those factors: energy output, reliability, and cost. And one more is the environmental impact. Okay, that is a big consideration as well. So some types of energy resource may have a good energy output, but they may have detrimental impact on the environment. They may cause damage to the environment that isn't good for the planet. Okay, and that's going to play a factor. So that is why we're looking at what energies we have and what energy resources we can use. Okay. Wind powers are ugly as a disadvantage. I wouldn't use the word ugly, but you're right. The word you'd use is like an eyesore, okay, or visual pollution is the term we'd use. But you're correct. It's about it's about how it's not a good look. People don't like it. If it's near them, then you don't want it like in front of your house, right? And say you've got a nice garden and you've got a wind turbine there, you don't want to see that. So yes, that is valid. Okay. Okay, so then I want to go and compare a couple of examples here. Okay, so the first one, let's say for a non-renewable source, I'm going to pick the first one, which I think was fossil fuels. Correct. Okay, so looking at this, let's see. I'll get my highlighter. So it says fossil fuels, a good advantage is readily available. Okay, so that means there's lots of it around. There's plenty of it there. You can use it straight away. Yeah, so that's a good thing. It's availability. If it's available, that means it's reliable, right? It's always there. It is a reliable resource. Okay, so that's a good thing. Then we talked about high energy density here. That is a reference to the energy output. So like I said, energy output is important. You need a high energy output to provide enough to the country. Here, fossil fuels per kilogram emit a lot of energy when you burn them. So it has a high energy density. Then the other factor we've mentioned here, cost. In this case, it comes to an advantage. In some cases, it can be a disadvantage. Okay, so here, fossil fuels are quite cheap to purchase and source. Okay, so that's why it's a good advantage in this case. And also here, I've talked about reliability. Okay, being reliable, it can meet the energy demands quite well. We don't have ups and downs in it. It's a constant energy output. And here you can see a big disadvantage for these non-renewable. Yeah, they're going to run out. Eventually, coal, oil, and gas are going to run out. So we need something to replace them. That's why it's a big disadvantage. And then, as I mentioned in my factors before, environmental impact. For non-renewable sources, this is often a disadvantage, especially fossil fuels. Okay, the key thing being that they release greenhouse gases. Okay, that's a big problem, isn't it? It causes global warming. It's heating up the earth. It's a big problem in the environment. So we're trying to reduce that. So we want to try and move away from fossil fuels for that reason. And therefore, also, it can lead to water pollution. So that's another environmental impact. And also health risks, yeah, impact on the environment. People having what they say respiratory problems, so things like breathing issues and stuff like that. Okay, so those are all your environmental impacts. If you think about energy, cost, reliability, and environment, think about those, and you should be able to get advantages and disadvantages for each. Okay, so those are your prompts in your mind, is what I was referring to. So that's one non-renewable. I want to compare it to a renewable energy source. Okay, so the one I want to pick, geothermal. So for those of you that don't know what geothermal is, the easy way to remember it is split this into two parts, geo and then thermal. Okay, the geo, we've all studied geography. Geo is to do with the earth or the ground. Okay, so I'm going to say geo for ground. And then thermal, anything thermal, we're talking about heat, warming things up. Okay, so I'm going to say heat for thermal. So geothermal is essentially ground heat, heat from under the ground. Okay, so I see people mentioning break. So we're just finishing now. Give me a couple of minutes. Obviously, I had the intro, so I'm just finishing in maybe 2 to 3 minutes for the combined science people, and then I'll need a couple more minutes for the triple people as well to cover that one section. But don't worry, you will get 15 minutes, and I'll notify you when we're going to rejoin as well. So you will get your 15 minutes. Don't worry about that. So geothermal being ground heat. Okay, so how easily the heat from the ground is used to create energy to provide electricity. Okay, so the good thing about it, environmental impacts here, clean and renewable, never runs out, and it's clean. It doesn't produce any bad outputs like greenhouse gases. It doesn't produce any. Yeah, very little greenhouse gas emissions. So that's a positive in this case. Remember earlier we saw it as a negative. So that's why I say think about environmental impact. It's either going to be good or bad. Okay. Then reliability. Yes, it's reliable in this case. The heat from the ground is a constant amount of heat from all the time. It's not varying. Yeah, not like the heat from above the ground. But underground is very constant from the core of the earth. Cost, financials. Yeah, it's a low operating cost. It's very easy to set up. Very easy to maintain. Right, you plug it, put pipes in the ground. It heats up the water, and then we get energy from that. And also environmentally, it doesn't take up much land, so it's not taking up much space. You can build around it. It doesn't use up the land or damage it too much. Okay. Disadvantages. You need somewhere where the heat from the ground is easily available. That's an environmental impact. Okay, geographic availability, again, environmental. Cost, here's an example. It can be good, it can be bad. In this case, it's good once it's running, but it's expensive initially. What we mean by that is it's expensive to build one from scratch because you need to dig deep underground to get the heat. Okay, and then again, environmental impact in other ways, not greenhouse gases, but here, maybe water pollution. Yeah, so that can cause issues with the system because as water runs through this power plant, it can then go and be removed into like rivers and things, which cause harm to any fish and things that may live in the rivers. And then going into the ground, another disadvantage I mentioned is causing the ground to shake. You can lead to an earthquake. Yes, that could be a disadvantage as well. So again, those 4 factors. Talked about energy output, we talked about reliability, talked about cost, and we talked about environment. Always those 4 things. Okay, so if you think of those 4 and you think of how is it good or bad for each energy resource, that's going to help you with any sort of long 6 markers you may get for these types of question. Excellent. So in the rest of that, you can see I've gone through all of those and there's different methods. And then there is the specification. So it brings us to the end here. We've got some questions here for you to try. Obviously, we've reached the hour. This is for something for you to look at later on, but it covers everything we've covered in this topic. So hope that was good. I know it's a bit of a push through. Yeah, like I said, it's very, very content heavy. We want to get through as much as we can. So doing our best there for that. Have a read through. Obviously, we've got these notes written for you, so you have this guide prepared. And then for those of you that are with us for combined, you may leave now. Okay, it's 11:05. I'm going to say if you leave now, please can you come back for 11:20? I will drop a message in the chat once I finish this. So for those of you on combined, thank you very much. I will see you at 11:20. For those of you that are doing triple, bear with me for a few more minutes. Literally a very small bit that you saw earlier on triple only. It's this experiment on investigating insulation. Okay, so this on the back of the required practical we did earlier for specific heat capacity. For those of you doing triple, there may also come a question on investigating insulation. Okay, so here, where with the specific heat capacity, we were heating up the substance and then working out the specific heat capacity of it. Here, we have something that is already hot. Okay, so in this experiment, you have hot water already in a beaker. Okay, and we're going to investigate how the insulation around it, sorry, didn't want to draw that, just wanted to highlight it, how the insulation around it affects how well it keeps in that heat. Yeah, so whether does the water cool down faster or less depending on the insulation. Okay, so we're looking at two things: the amount of insulation. So you can see here, we're looking at how the thickness of insulation affects whether it heats, how quickly it heats up or cool down. And then we're also looking at the material, the type of material. Say if you use wood or compared to say if you use wool, which one's going to be better? Yeah, in your head, I'm sure having done it, you probably know the answer, but the experiment is used to investigate that. Yeah, maybe like felt compared to wool, compared to, so different types of insulating material. So the thing, like someone mentioned earlier, they were talking about dependent and independent variables. But there's some that we call control variables, right? To keep the experiment consistent. The amount of water, the temperature of the water to start with, the lid on the top to make sure no heat goes through the air on the outside. Those are all things we keep constant, okay? Same volume of water and the same temperature, initial temperature of the water. So we have the thermometer in there to record the initial temperature. We place the insulation around it and then time it. We set a time of say 5 minutes, 10 minutes, and then record the temperature at the end. The better the insulation, the less the change in temperature, isn't it? It's going to stay as hot as possible. If it's not a good insulator, the heat's going to be given off to the surroundings. The drink is, or the water in this case, is going to cool down. So the comparisons that you get as a result is that the thicker the insulation, so if we're talking about comparing the amount of insulation, the thicker it is, the smaller the temperature difference. Yeah, it's going to keep in heat better, isn't it? The thicker it is. So even like wearing your clothes, you wear thicker clothing to keep yourself warmer because it keeps your body heat in. The other type is the type of material. So there you get a result and you see the smaller the temperature change, the better the material is. Yeah. So like I said, comparing wood and comparing wool is going to be a better insulator. Yeah. So that's another comparison they'll give you. So those are the things they look for in this experiment. Again, if you're talking about the 6 marker, like we said, 2 marks for equipment. So thermometer to measure temperature, same volume of liquid is very important, using a lid to prevent heat transfer to the surroundings, and then talking about the material type, making sure you change the material either in thickness and repeat the experiment, or you're changing the material and repeat the experiment. You can also mention repeating the experiment several times for each type of material or each thickness to make sure you get an accurate or reliable result. For this topic, there aren't any particular memory tricks that we have. If you think of any, please feel free to let us know. But at the moment, it's just the key points that I've given you in notes and how to what to think of when it comes to those 6 markers. What steps to think of: apparatus, method, and then results. So 2 marks, 2 marks, 2 marks, or 3, 2, 1, something like that. And then the points I mentioned about 6 markers for energy resources. Again, that's different types of energy transfer, energy resource, having dependent on cost, reliability, energy output, and environmental impact. But yeah, that's it. So, sorry, I'm going to cough in a minute. So we'll leave it there. It is 9 past. Sorry to give you 4 minutes less than the others, but we'll see you back at 11:20. Where we were going to topic 2, which is on electricity. So look forward to seeing you there. Thank you, guys. 1 down, 3 to go. 1 more till lunch. Keep pushing through. And I hope it's going to be a valuable session. I'll see you in a bit. All right, guys, welcome back. Can you hear me? Everyone hear me okay? See me okay? Hopefully it's all good. Get a hello. Welcome back. Yeah, wicked. Okay, thanks, Philip. Cool. One session down. Stopped coughing now. So I'm back. Ready to talk for another hour. So 11, just after 11:20. Wicked. Good weekend here. Brilliant. So the next thing is I want to show you something before we get into chapter two. Topic 2 is not a story. And that is our cram classes. Okay, so did this last year, we're doing it this year. Before the night before every exam, we're going to do a cram class. Okay, I'm going to share this link now in the chat actually. So let me share this now. What we would like you to do, just as a bit of fun at the end of this session, we're offering the chance for one of you to get free access to this. Okay, currently paper ones will be free, just like they are at the moment for the cram classes, for the paper classes that we got, these Easter Bootcamp, sorry. And the paper 2s are £10 each. Just like that, the same thing for the cram classes. Paper 1s are free, paper 2s are £10 each. However, if you book your spot, now with the link I've just sent, go to book your cram spot, takes you down to the bottom here where you can sign up, okay? And if you sign up, then you will have a chance to win paper 2 for free. We're going to spin the wheel at the end, okay? But we have until, I'm going to say, till the end of lunch, okay? So I'm going to remind you at the end of this session as well. Sign up to this, and at the end of lunch, we're going to build the wheel with all the people that we've got involved. And then at the end of the session, I'm going to spin the wheel, and one person who lands on is going to win all of it for free, okay? That'll be paper 2 of the Easter Bootcamps and paper 2 of the cram classes, all free. So if you join this link, take a look, click on book your spot, get your name in there, and we will create the wheel and we will see who wins at the end of today, okay? So make sure you sign up. Cool. So with that being said, let's get back into our main part of this topic, which is electricity, okay? Make sure that we know everything on here, a lot more memory tricks, okay? Plenty of memory tricks to come. FRL classes, yes, you already have it. Sorry, guys. It's involved, it's with FRL classes, but not FRL Pro, okay? And where is it? When you sign up, when you book your session, you will get a link that will take us to the class the day before the class, okay? So you'll get that in your email. So make sure you sign up, you'll get access to that, and then you'll be in with a chance for the spin the wheel at the end where we will reveal someone who wins everything. Cool. Okay, this is a longer topic, so obviously we ran a little bit over on the first one, but I'm starting a little bit kind of, I guess, at the same time now. So we'll try and push on this. There is one topic for the triple guys at the end, which is on uniform fields, etc. So we'll get onto that. But electricity. So the first thing we look at, electricity symbols, the circuit symbols. Okay, you need to know these so that you can make sure you can draw circuits. Sometimes they ask you to put a circuit together, and you need to know how you connect things together as well. Okay, so what I've done is our first memory trick, some ways to remember some of these things here. Okay, so there are ways in which you can remember how these look and why they look as they do, okay, and what their functions are. So the first one, hopefully everyone knows what this is. If you don't, obviously you've got the revision guide above, you can take a look, but this is a cell, okay? How do I know that this is a cell? The way to remember it is SCE, but the LL here is like 2 lines. You can see what we've got there. We've got 2 lines here, don't we? 1, 2. That's like an LL. So an LL for cell. Okay, that's one way to remember it. The next one, we've got 2 cells. So when you have 2 or more cells in parallel, not in parallel, connected to each other. Okay, so they're all connected, one after the other. You can see here, we get multiple cells form a battery. Now, how do we remember what a battery looks like? So with the 2 lines now, each of these cells, we can see, comes with a big line and a small line. A big line and a small line, okay? Those lines can be put together to form a T. Big line and a small line, big line and a small line. The 2 T's making up the word battery, okay? So when you got one on its own, it's 2 L's for cell. When you got multiple of them together, they make T's for battery, okay? So that's the way you can remember a battery. Nice. People know it already, Jafona, good to see that you know it. And then the cell is for 2 individual lines. The battery is for multiple cells. Okay, the next one, an ammeter, okay? Given the letter A, an ammeter is used to measure the current in a circuit in amps, okay? Now, the way you can try and use a memory trick for this, I'm going to say is if you have this, look at the letter A, okay? What I'm going to say is take the line across it and put it down at the bottom here. If you move that down, you form a triangle. The key thing about that is a triangle is a full loop, isn't it? You can keep going around the triangle like this. That's important because the current goes in a circuit in the loop, and an ammeter is connected in that loop in series. Okay, so it's connected into one loop, it's connected in series. So that is the key thing about an ammeter. So you know that you connect an ammeter in series because it all fills in one loop. So that's what I'm going to put here. Full loop. So that means an ammeter is always connected in series. Okay, now that's for an ammeter. What about the next one, a V? A V stands for voltmeter. What exam board are the cram classes for? Same thing as this. They're AQA based, but there is much crossover between all the exam boards. Yeah, at least 70% of it is the same. It may be split slightly differently between the papers, but this the topic content, there is a very significant crossover between them. Parallel, Frozen has got what I was going to say. Yes, Jathuna knows it is a voltmeter. Dennis, why does it always have to be in series? It's just a rule for the way it's connected. It won't measure the current unless it's in series because current flows in the loop, right? If you measure it somewhere else, it's not going to be in that main loop. So the current is in series, okay? When it goes in components, it goes through them, not across them is what we say. But an ammeter, just a rule to remember, it's always in series. A voltmeter is measuring, someone said the word parallel, correct? Okay, how do we remember that it's in parallel? Look at V. V is essentially two lines. So these two lines here. Yeah, so two lines, but they're next to each other. So we take those two lines in a V, bend them out like this, and we get two lines that are parallel to each other. That's the way to remember it. Yes, I put V like that in red, made up of these two lines. Yeah. So that means that a voltmeter is always connected in parallel to the component. So usually in a circuit, if they're saying measure the current and potential difference of a light bulb, the ammeter will be in series with the light bulb in the same loop, and the voltmeter will be in like a branch just around the light bulb in parallel. Okay, so a voltmeter is always connected in parallel. Okay, and the last one, again, someone has mentioned it here already. It is a diode. Yeah, so a diode, the key property of a diode is it only lets current flow in one direction. Okay, the way I'm trying to remember that here is look at this green. This green part of the diode is like an arrow, isn't it? It's pointing in that direction. So we're saying that it allows current to go this way. So we give that a tick. But then the second part of it is a straight line. It's stopping that arrow, isn't it? It's stopping the arrow from moving past it. It's stuck there. So it doesn't go the other way. It stops it going the other way. So the red for the line is a no-go. Okay. So the key thing here, a diode only lets current flow in one direction. Okay. Now, those are the key ones I wanted to kind of show here. But obviously there are several. You can see them at the top here. You've got resistors, different types of resistors, a light dependent resistor, thermistor, a couple of which we're going to see a bit later on, and a variable resistor, which we're going to see as well in an experiment. Yeah, we had one required practical in the first topic. For those of you in combined, we're going to have another required practical here. But those are your key circuit symbols and a few memory tricks for certain ones and how they're assembled in a circuit. Yeah, especially the ammeter and voltmeter. People get that wrong in an exam. So I just want to make sure people know how that is connected. Okay, so moving on. Electrical charge and current. So in this topic, this is the first of which we're going to see an equation. There are several equations in this topic as well. It doesn't stop. The equations continue. Your equation sheet is pretty big. There is a lot in there. So electrical charge and current, how does it work? So charge is basically how the electrons in a circuit flow through it, okay? And current is the rate of flow of those electrons, that charge, okay? So current is the rate of flow of charge. So I will put that just in red here. So current is the rate of flow of charge. Okay. So that in itself, we talked about rate, didn't we, earlier? Yeah, in the previous topic. Rate is to do with something changing over amount of time. Yeah, so how much time it takes to do something. In this case, it's the rate of flow of charge. So it's the flow of charge over time, okay, or current over time. So if you rearrange those together, how much charge flows over a particular time? Current is charge over time. That's what we've got here. If I cover up current, if those of you haven't seen this before, this is like an equation triangle, okay? And what you do is you cover up the one that you don't know. So say I don't know current. What is current equal to? It's the other two. Charge Q divided by T, time. Yeah, Q over T. If I want to find the charge, which is the letter Q, that's the symbol it's given in an equation. If I cover up Q, I and T are on the same line, so we multiply them. So Q equals IT, okay? And the way I remember the equation, Q equals IT, as you can see here, I'm going to put the word quit. Yeah, it just basically sounds like it's just an I missing in the middle. QIT, quit. Yeah, Q equals IT. It's a good way to remember it. Charge is measured in coulombs, again, by the scientists that found out about it. Amps or amperes is the measure for current, and time in seconds. We saw it earlier. Time is always measured in seconds. The other thing I wanted to mention is about electrical current, okay? Here we've mentioned current flows from the positive terminal of the battery, positive being the longer line, to the negative terminal, okay? So we know positive is like two lines like this, isn't it? So it makes a long line. Negative is just one line, so it makes the smaller side, okay? So the smaller side of the battery, the smaller line is negative, and the longer line is the positive terminal, okay? Current is the rate of flow of charge, so everybody got it. That is what the definition is, yeah? So why do we learn conventional current if it's wrong? It's what you're taught at this stage. What we're trying to show here, and what I was going to mention, is the difference between which way current flows and which way electrons flow. They're two different things, okay? So just to establish, current flows, as we've shown here, from positive to negative. So I'm going to say on the left-hand side, current flows away from the positive terminal towards the negative terminal, okay? So from positive to negative. Electrons, charge of electrons, they're negatively charged, okay? So when we look at charges, which we're going to see a little bit later on, they are like charges, like magnets, like charges repel, okay? So they're going to go away from the negative. They don't want to be near the negative. They want to be attracted to the positive end. So electrons actually go in this direction, from negative to positive, okay? So I'm keeping the green arrows there, and I'm going to say electrons flow from negative to positive. Yeah, so that's the difference between them. But conventional current, or current, is flowing from positive to negative, okay? So that's the key difference there. So we've spoken about the equation, we've spoken about what current is, what charge is, and how they're related, okay? So that's an example there. You can revisit the equation as well. The next thing I wanted to get into was current, resistance, and potential difference. So a big part of this topic, okay? And how they're all related. So current is, as we saw earlier, the rate of flow of charge. But what is potential difference? So potential difference, sometimes people use the word voltage, but potential difference is basically the rate of energy transfer. Okay, again, I'm using the word, sorry, not the rate, sorry. It's the energy per unit charge. Okay, so it's the amount of energy that you transfer per unit charge. So I'm going to highlight that here. That's the important thing. I'll zoom in a bit. The key thing here, the definition again for potential difference, it can come up in your exam. It's the energy transferred per unit charge. Okay, now that is, so through a light bulb, the potential difference of the light bulb is that how much energy is transferred through the light bulb per unit charge that it receives from the circuit. So there we have the definition for that. And then resistance is basically, as the name suggests, if you resist something, you're stopping something. Yeah, in this case, resistance is trying to slow down the flow of current. So I'm going to underline that here. Resistance slows down the flow of current. The greater the resistance, the more it stops the current flowing, so the current decreases. It's a lower current, okay? So they are not proportional to each other. They act in opposite directions, okay? So the lower the current, the greater the resistance is stopping it. However, the law that's come up with is Ohm's law, okay? Ohm being the unit for resistance. You can see here the units for resistance is ohms. Now, Ohm is a scientist who discovered this relationship, which is the relationship between potential difference and current. So what they're saying is the potential difference and current are directly proportional. Okay, they are directly proportional unless there is a physical change. Okay, the physical change can then lead to a change in resistance. So if you're obeying Ohm's law, hence Ohm, the resistance stays the same. Okay, it's constant. So that's what Ohm's law is telling us. Okay, so I'm going to put here, just as a reference, constant resistance is what this then means. Because then if the resistance is constant, the relationship between potential difference and current is directly proportional. Yeah, so the potential difference across a component is directly proportional to the current that goes through it unless there is a physical change. When's the spin the wheel? Yes, someone's answered it. Thanks, Calais. It's the end of this session. So right at the end, just before we wrap up, we will spin the wheel. Okay, so an important point here, a conductor is basically an electrical component that obeys Ohm's law, so that shows this directly proportional relationship, is called an ohmic conductor. Okay. That's what that is here. So we've underlined that. So if we have that directly proportional relationship and a constant resistance, it leads to this equation. This is Ohm's law's equation. Potential difference equals current times resistance, or V equals IR. Okay. And again, there is another triangle here. So if you cover up the one you want to find, say I want to find the current, I cover up current in my triangle, then it gives me the equation current equals potential difference over resistance. If I want resistance, I cover that up. It's potential difference divided by current. Or if I want the potential difference, as we said, V then equals IR, I times R. Okay, so those are the relationships. Does this link to the three graphs, faceless truth? You are correct, it does. And later on, I'm going to show you, I've got a couple of memory tricks to try and remember how they work and what they look like. Okay. Excuse me. What does obey mean? Obey means it follows. Yeah, it basically follows Ohm's law. So, you know, when you obey, you're obedient. It means you listen, you understand. Yeah, it follows. So you have exactly complies to exactly that. Good. So then again, I've got another example. Please take a look of just applying it in a simple equation, how to use the equation in a question. Okay. So V equals IR. You may then need to rearrange depending on the question. Here, it's asking for current. Find the current. So then you cover up current in the equation. You want V over R. V in the question is 12 volts. R is 0.6 ohms. Therefore, V over R. Okay, so that's an example of using the equation. Okay, so that's those two. The next thing, required practical. Okay, the first one, required practical. This time is for investigating resistance. So again, I mentioned it in the first session. Explain or identify the apparatus, state the method, so the procedure, what steps you're taking, what measurements you're taking, and then evaluate your results. Last time, it was a calculation for specific heat capacity. Here, we might see something different. Let's see, okay? So, the experiment here is to look at how resistance in a circuit is influenced by two things. Yeah, so this experiment can be one of two, and I'm going to highlight them here. We've underlined them. The length of wire is one experiment. Yeah, so how the length of wire affects the resistance, or another one is how the combination of resistors affects the circuit. So having one resistor compared to two resistors or three resistors in a circuit, yeah, how that affects the resistance. So, sorry, if we want to measure the resistance, I'm going to scroll up quickly. We saw it in an equation, haven't we? Potential difference V equals IR. We want R. So if we want R, we're going to need to know the other two in this equation. So that is V and that is I, potential difference and current. So linking that earlier, what do we measure those with? We measure current with an ammeter and potential difference with a voltmeter. Secondly, how do we connect them? We spoke about that as well. An ammeter in series and a voltmeter in parallel. So those are the points I've mentioned here. Okay, so measure the current using an ammeter in series, measure the potential difference using a voltmeter in parallel. So already you're building up those marks. That's two pieces of apparatus and explaining what you're measuring from them. So already that's like three, I would say 3 marks, maybe even 4. Okay, so you measure those, and here is where it splits off into the two types of experiments. Sorry, the first experiment being for the length of wire. Okay, so what we do is we have a specific length of wire. Let's say it's 20 centimeters long. Okay, how do we know that? Measure it with a ruler. So that's our third piece of apparatus. Okay, then how do we vary that length? We connect a fraction of that length at a time by connecting it with crocodile clips to the rest of the circuit. I'm sure everyone here has used crocodile clips in an experiment in physics at school at some point. Crocodile clips connect different components in the circuit. Yeah, and this is what the component we're investigating. The wire, we're going to put it at different lengths. Okay, so let's say on here, I've measured it up to almost 20. Altogether, it's the full length of the ruler, 32 centimeters. But I'm going to do this in parts. So let's say I did it every 5 centimeters. So I had the crocodile clips here and here. I keep this one fixed and I move the second one. So I start it at 5, then I repeat it at 10, then I repeat it at 15, and I repeat it at 20, 25, and 30. Yeah, so I have a variety of different lengths. Every time I do that, I record my current from the ammeter and I record my potential difference from the voltmeter. That's what we're doing. Okay. So should the ammeter be before or after a component, and why? It doesn't matter. Correct. Yeah, I think someone's mentioned it. Yeah, it doesn't matter as long as it's in series. Yeah, so it's included in the same loop as the component. Which it is here. The component is the wire in this case. That's in series, isn't it? They're in one loop. Yeah, so that means the ammeter is in series. The voltmeter, you can see, is in a separate branch. They're in parallel. It's a separate loop, isn't it? Compared to the main loop with the battery, the voltmeter is parallel, so it's connected in that way as well. Okay. So those two are the way you do it. So now that's set up, we then measure at various lengths. So here we go. I've said, e.g. every 5 centimeters, and then note down the current and the potential difference. Okay. Then we move the clip to the next length. I said 10 centimeters, repeat it. Repeat for various lengths. So I said every 5 centimeters up to say 30 centimeters. And then once we've done that for every single length now, we've got potential difference and we've got current. And we saw earlier, V equals IR. So again, interpreting your results time, use those to calculate the resistance. Each time V equals IR, get the resistance. So then now at every single length, 5, 10, 15, 20, 25, 30 centimeters, we have a corresponding resistance. So now the second part of interpreting is now we're looking at, remember the experiment is how does resistance is affected by the length of the wire. So we look at length on the x-axis because that's your independent variable, the one we've changed. And how is that affecting the resistance? So we look at that on the graph. We plot resistance on the y-axis, length on the x-axis, and we put our various points. And then you can see there's a pattern forming. Yeah, so we determine that pattern by drawing what we call a line of best fit through the component, through all the points. Yeah, and you can see maybe a couple are to the right-hand side of the line and a couple are to the left-hand side or above the line. So overall, it's kind of balanced. It's a line of best fit. Okay. So some people are saying, is it a linear relationship or directly proportional? Very good question, that actually. The difference between those, I'll cover that right now. It's a really good question. A linear relationship is when it's a straight line, okay? Directly proportional is when it's a straight line, but it goes through the origin. That's the important difference, okay? So for example, if I had a line that looked like this, it's a straight line, but it's not through the origin, isn't it? It's here. So that's a linear relationship. But it's directly proportional is the line we have on the drawing already. It goes through 0, it goes through the origin. That's the difference. So I hope that helps you. That's the difference between linear and just saying it's a linear relationship and saying it's directly proportional. Okay, linear does not go through the origin. Okay, so that's for those. So that is for how you do it for an experiment for the length of wire. Yeah, so a 6 marker, you can see measure the length of wire with a ruler to a certain point, e.g. 5 centimeters. Connect it with crocodile clips. Measure the potential difference and measure the current, yeah, using an ammeter and a voltmeter respectively. You're already on about, I'd say there, 3 to 4 marks. Then repeat the experiment for different lengths. So let's say that's 3 marks. Yeah, so measure the initial length, record initial length, record a potential difference, record a current. Then change the length and repeat the experiment. So that's another one. Then at each length, calculate the resistance using V equals IR. That's another mark. That's 5. So now we've got all the lengths and all the resistances. Plot a graph of length, resistance against length. And then you have your 6 marks. Yeah, and that's how you carry out the experiment. Then the next question might say, what do you see with your results? So that's how you split it up into 6 marks. So let's look at the similar one, but for now investigating resistors in series and parallel and how combinations affect the resistance. Okay. This time we're going to start with do the experiment, but for 1 resistor. Okay. Then repeat the experiment for 2 resistors, and then for 3, and then for 4. Yeah, so maybe 3 to 4 is enough. But repeat the experiment, but this time instead of changing a length of wire, you're adding a resistor each time. That's the difference. Yeah, so if you follow the steps here, you can see For the first circuit, note down the potential difference in the current using the ammeter and multimeter, and then calculate resistance. All the same as last time, V equals IR. Yeah, those 3 points, same in both experiments. The difference now comes when you change the length. In the first experiment, you now connect the second circuit, it says here. Yeah, so the second circuit being connecting another resistor in series, and then repeating the measurements, potential difference, current, and calculated resistance. Then it says the third circuit, repeat it one more time. So this time in parallel, okay? So put the resistor 1 and 2, they were in series, now branch them off, and now measure the current potential difference and calculate the resistance. And then you can see how adding resistance in series affects the resistance, and then how potential difference, how putting them in parallel affects the resistance, okay? And that's the key difference here you're going to spot, is in series, combining the resistance, it equals to the sum of the individual resistors. What do I mean by that? If, let's just say, every resistor I add here is 2 ohms, okay? So this is 2 ohms, this is 2 ohms, and it's the same 2 ohms, but I put them in parallel here, okay? If it's in series, it means the resistances add up. It's the sum of the resistances. So when I have 2 resistors in series here, the total resistance here is 2 plus 2, which is 4 ohms. That's what you see in series, okay? So if the resistance goes up to 4 ohms, remember we said earlier, an increase in resistance reduces the current. Less current can flow through because there's more resistance against it flowing, okay? That's for series. So the combined resistors in series increases because it's the sum of the total resistances. In parallel, okay, it says a combined resistance in parallel is less than the sum of the 2 individual resistors, okay? So the total resistance in parallel is actually less. You'll find it's less than 1 individual resistor, the smallest one. So it'll be less than 2 ohms will be the answer for the total resistance. So in parallel, the total resistance is less, so more current flows through. So this is why when you have, say in your house, you have loads of different light bulbs in your different rooms in your house. They're all connected in parallel so that more current can flow through the circuit and reach all the light bulbs in your house. So that's a practical use of why you would put resistors or components in parallel instead of in series. And also, if one light bulb turns off in your house, the other ones will stay on. If you had them in series, one cuts off, all of the circuit stops working. You don't want that. Yeah. So the rule for parallel is it's the total. You don't need to know how the equation works, but there is an equation that when you sum them up, it becomes less. What you need to know for GCSE, the key thing is the total resistance is less than the 1 individual resistor. Okay, that's the key thing to remember. You don't need to know why at GCSE. You do need to know at A level, but I'm not going to. I can just say to you here, it's the way you work it out, the total. You don't just add them. It's actually summing up what we call the reciprocals 1 over. Okay, you don't need to know that. You just need to know that the total resistance is equal to the sum of the total resistance is equal to less than the lowest individual resistor. And that is because, yeah, as Octopus says, the current is shared between the resistance. The current flows through each of the components more. Okay, because it splits off, it allows more current to flow through each section. Therefore, there's less resistance overall in the circuit. That's why. You don't add it in. They're not going to ask you a question to add it here. Okay, they will ask you to work out the total resistance, but to do that, you'll just need the total voltmeter reading and the total current reading. You'll get that from this, and you'll get that from this. And using that, you can work out the total resistance. V equals IR. That's how you use it. Yeah. So, based on that, those are the 2 types of experiment. Okay, and based on that, we can see. So sorry, I'm just reading some of the messages. If current is shared in parallel, is there a larger total current? It will allow more current to flow through the circuit. So you will see more current. I'll quickly go back. The ammeter reading in this circuit for 2 in series will be less than the ammeter reading here. That's what you'll see. Exactly. Faceless truth, the difference between linear and directly proportional. Linear is a straight line that doesn't go through the origin. Directly proportional is a straight line that does go through the origin. That's all I said. It's the only difference. Yeah. Linear is a straight line not through the origin. Directly proportional is a straight line that goes through the origin. That's it. Okay, the next bit here, IV graphs. Okay, how are we doing for time? Okay, cool. IV graphs. The different types you can get. Okay, there's 3 types of graphs, and that's what I'm going to go through here with ways to try and remember them. Okay, the first one is an ohmic conductor. The second one is a filament lamp, and the third one is a diode. Okay, there are also graphs showing how resistance varies for a LDR, light dependent resistor, and a thermistor. All of those I'm going to cover here. Okay, so I've drawn them all out and I put red for the lines to kind of try and explain why they look like that, or how to remember that how they work. Okay, so an ohmic conductor, as we said before, is a component that obeys Ohm's law, doesn't it? Okay, so ohms, yeah, it's Ohm's law, because potential difference and current are directly proportional. How do we know that? Remember, directly proportional goes straight through the origin, which this line does. So it's a straight line. Okay, so ohmic conductor, straight line through the origin. And always, not origin, I don't know why I've written that, origin. Okay, so with ohmic conductors, they're things like a fixed resistor or a fuse or something like that. So anything like that, they have components that are made up of straight lines. Okay, so let me draw the components here. For example, a resistor is like this, a rectangle with a line through it. A fuse is like a rectangle, but the line goes straight through it. Both of those are straight lines as well, aren't they? All made up of straight lines, straight. So that's the way to remember it. Ohmic conductors are a straight line because they're made up, components are always made up of straight lines. So I say here, made up of straight lines. Okay, the next one is a filament lamp. How do you remember the curve? The curve is like an S-shaped curve. Okay, what does a lamp do? A bulb shines, and shines starts with an S. It shines, and that's what gives that S shape. Yeah, so let me curve that off a bit better. There we go. A bulb shines, so then you get this S shape. Okay, the key thing to remember here, why does it have that S shape? The key thing is there's a physical change. Okay, a physical change here being in a filament lamp, when you put your hand near it, you can't when it's on because it gets hot. You can't touch it. You briefly touch it and you might like almost burn yourself because it's super hot. Okay, so what happens is it tries to obey Ohm's law to start with. You can see in this section it's kind of straight, then it curves off here, and that's because it gets hot. When it gets hot, remember, electrons flow. That's what causes current in a circuit, isn't it? It's the flow of electrons in a circuit. So that flow is now being disrupted because the filament lamp warms up, the electrons gain that heat energy, and then they start to vibrate. They get excited, they vibrate around. If they're vibrating next to each other, they're all going to bump into each other. So instead of flowing in a smooth line, they're now all going to bump into each other, and they're not going to flow as smoothly. So the resistance goes up. Okay, the resistance going up means that no matter how much you increase the potential difference, the current will plateau off. Remember, we said an increase in increase in resistance means a reduction in current. So the current kind of levels off, and then the current doesn't increase anymore. So that's why that happens. Filament lamp gets hot, electrons vibrate, resistance increases. Okay, and that's the difference here. The next one is a diode. So we mentioned earlier the key property of a diode, it only lets current flow in one direction. Okay, so you can see here on the negative side, it doesn't move anywhere. It's flatlined at zero. It's only once you get past positive and you get here, there's just a small point just after zero, not quite at zero, it turns on. And then it's what we call linear. Yeah, it's linear from here. Yeah, before zero, before it switches on, it's not moving. Current doesn't flow at all. But then once it reaches this point, which we call its switch on voltage, or switch on potential difference, it then activates, it turns on, it allows current to flow through, and then the relationship is linear after that. Okay, so a diode, we mentioned it earlier, only lets current flow in one direction. So those are your three what we call IV graphs. Okay, the important thing to note here, the gradient of the graph gives you 1 over the resistance. Okay, why is that important? Because I'll tell you what it means. So gradient equals 1 over R. Okay, 1 over resistance. Why is that important? Because then that tells you the steeper the graph is, okay, the smaller the resistance is. So if it's steeper, it means there's a low resistance. If it's shallower, like here, where it's flat, that means resistance is really high because the gradient is going to be really small, getting close to zero. Zero gradient means a flat line, meaning super high resistance or infinite resistance. Okay, so I'm going to say here that means that steeper gradient, or just to save me writing, the higher the gradient, the larger it is, the steeper it is, the lower the resistance. That's the relationship. Okay, that's what the gradient of an IV graph is showing you. That's what these are, IV graphs. They're called IV because it's current against resistance, current on the y-axis and potential difference on the x-axis. So you always mention the first letter first, current against resistance, IV graph. Filament lamp and bulb are exactly the same. That is correct. All good. Which part don't you get? Please let me know if it's not the same or not. Why is it not changing y over changing x? It is. It is. The gradient is. Okay. I'll show you briefly why that's the case. Change in y. What's the y-axis? It's I, isn't it? Yeah, so I'm going to say the gradient equals, so m equals, like you said, change in y over change in x. Instead of y, what's on the y-axis? I. And on the x-axis, you can see there is v, so it's I over v. Okay? Our equation from earlier, v equals IR. Yeah, potential difference equals current times resistance. If I rearrange that, we want I over v, don't we? So I need to move R to the left-hand side and V to the right-hand side. So I divide both sides by R and by V. So that gives me 1 over R equals I over V. That's where it comes from. That's why the gradient is 1 over R, 1 over the resistance. Yeah, because change in Y over change in X on an IV graph. Okay, so all you need to know is that on an IV graph, the steeper the graph, the greater the resistance. Yeah, so I'm going to take out the bits that you don't need to know. The bit you really, really need to remember is this. So I'm going to draw the arrow straight from here. The steeper the line, steeper the gradient, the lower the resistance on an IV graph. Okay. That's what I would do. Okay. If you're going to calculate resistance otherwise, you'd use V and I and use V over I equals R. Okay. You take measurement, you take what the potential difference is, take what the current is, and use the equation V equals IR. That's how I calculate it. Exactly. Eliza, if the gradient is higher on an IV graph, the resistance is lower. Okay. Because I is on the y-axis and V is on the x-axis. So the gradient, the higher the gradient, the lower the resistance. Okay. That's what I'm showing. Okay, cool. So then there were a couple more graphs here, one for an LDR and one for a thermistor. So an LDR stands for light dependent resistor, LDR. Okay, so that gradient thing applies for all the graphs, yeah, for all those IV graphs. So then LDR, light dependent resistor, depends on light, as the name says. Okay, so what we're showing is the greater the light, the lower the resistance. As the light shines on the resistor, it causes its resistance to decrease and allow more current to pass through. Okay, so that's what we're seeing for a light-dependent resistor. And then for a thermistor, as the name suggests, a thermistor is like a thermal resistor. So it's resistance depending on heat. So that's why on this graph, I have temperature on the x-axis instead of light intensity. It's thermal, right? So that's to do with temperature. So the greater the temperature of the resistor, it causes its resistance to decrease. And you can see these graphs have the same shape, right? They have exactly the same shape. And I've said that L, you can see I've made the L in the shape of the curve here. So LDR, it takes that shape like a gradient going down, okay? And they both have the same shape. Cool. So those are your different types of graphs that you need to know, okay? They may ask you to draw them, and they will ask you to explain them. The filament lamp one is super important. So if you want more of an explanation, again, you can see it here in the notes. But I talked about the temperature rising, causing the electrons to vibrate, and therefore resistance to increase. Okay. So those are your different graphs you can see here on the spec. Make sure you can read through it, make sure you're happy with it all, but that's all covered there above. And then you have a required practical for IV graphs as well. Okay, so there's 3 practicals we got here. We had one for length of wire and resistance, one for combination of resistors and resistance, and now we have required practical for IV graphs. So this is how do we test and get the graphs that we drew above. So how do we get the graphs, these 3? Okay, what's the experiment we do to carry it out? So you can see on the graph, we need I and V, hence it's an IV graph practical. Okay, so we need an ammeter in series, a voltmeter in parallel to the component we're testing. So we might change it depending on which one they ask for. They say, how do you find an IV graph for a bulb? You'll say, connect the bulb with an ammeter in series and a voltmeter in parallel. Switch bulb out for LDR, for diode, switch bulb out for resistor. You get the same thing. It's the same experiment. Okay, so put the component to be tested parallel to with a voltmeter in parallel and a current, an ammeter in series. The one important piece of equipment you need to mention here on top of that is the variable resistor that you see here. Okay, the variable resistor is a vital part of this. So I'm going to say put a variable resistor in the circuit. Okay, so what you do is you have that all connected. You then note down the potential difference and the current, okay, from the voltmeter and the ammeter respectively. Then a variable resistor is a resistor where you can control the resistance. So you adjust that resistance on the variable resistor, and then you take some new readings because the readings will change. Do that again a few times. Yeah, so change the resistance on the variable resistor, record the ammeter and voltmeter readings. Change it again, record the ammeter and voltmeter readings. Okay. And then also, if you want to see how it affects the other direction, because you can see on our graphs, you can see the results here, as we saw earlier, you have a positive section of the graph and also a negative section. So to get the negative side, swap the connections. Okay, that's an important point in this experiment. Okay, so if we're going for 6 marks, test component with current in parallel, current in series, ammeter in series, and voltmeter in parallel. Okay, then set the resistance of the variable resistor, record the current and potential difference readings. Now, then swap the connections. Yeah, then vary the resistance. So that's already, I've mentioned like 5 points, but that covers about, I'd say 4 to 5 marks. Okay, because in the last bit, you've got your current and potential difference, your I and your V, at different resistances, isn't it? Once you vary the resistor a few times, you have a few different I and V readings. Then you plot those points on a graph, on an IV graph, and you get your graph as your result. And that's your interpretation of results. Okay, so that's how you get the 6 marks in this. Guys, this counts as a revision. Of course it does. We're going through the whole topic. We're going through the whole of paper 1, every single topic, every single point you need to know. It's revision. Yeah, so you're making notes. I've given you notes as well, things to highlight, things for you to write. This is a revision. How do we need to know why a filament lamp decreases? Do we need to know? Yes. Sorry, Dennis, we do. This is what I explained earlier about the increasing resistance because of the increasing temperature. Yeah, so you do need to know that. They can ask you, why does the graph shape, or why is the graph the shape it is? And they may ask you that. And in this experiment, you're showing that, right? Because you're taking your different measurements, you're changing your variable resistance, variable resistors resistance, and then recording new values. And then for a filament lamp, you will end up with this shape. Yeah, that's the shape you get for a filament lamp. And then you're showing that that is an S curve. Okay, cool. So that is for the different types of graph. The next thing in circuits, series and parallel. Okay, so we have these two circuits in parallel. All the components are in separate branches, as we saw earlier, and you can see here. So 3 bulbs in parallel, 3 bulbs in series, they're all in one loop. Okay, so there is a way to remember this, and also how to remember the rules in a series and a parallel circuit. Okay, so I'm trying to break them down here. The first one, series. Okay, and you can see here, I've said in series, the letter R is the only word with a loop in it. Okay, so there's only one loop in the word. And in a series circuit, everything is connected in one loop. So that's the rule for a series circuit. Okay, so everything is connected in one loop is what I'm going to put here. So that's for the first thing. I keep getting the highlighter out. Can't fit it in. So here you go. All components connected in one loop. Yeah, so that's for series. And then in parallel, you can see here, I've highlighted with red circles, there are multiple loops. 1, 2, 3, 4 in this case, 4 letters with a loop in them. Multiple loops, which is what a parallel circuit is made up of. All the branches, there are multiple branches or multiple loops in the circuit. Yeah, so I'll put here components connected in multiple loops. Okay, so that is how the current and series and parallel circuits are connected. Okay, so now we have that. We're looking at what the rules are for current, potential difference, and resistance in those types of circuits. Okay, so for a series circuit, I've written it slightly different here this time, haven't I? I've put C for series instead of SE. Okay, because C for current, that is the thing that stays the same in a series circuit. So I've called it series because current stays the same. Anywhere in a series circuit, the current is always the same value. Okay. Then the next thing is parallel. So parallel, I've put a capital P because P also is for potential difference. And in a parallel circuit, potential difference stays the same. Okay. So here, in series, current stays the same. In parallel, potential difference stays the same. Okay, so that's for series and parallel in terms of current. So if one is the same, the other quantity is shared. That's the difference. Okay. So if in a series circuit, C for series, current stays the same. Okay. But on the flip side, potential difference is therefore shared. So if there are 3 components, 3 light bulbs, the potential difference is shared between those 3 light bulbs. But the current in the 3 light bulbs will be the same. If you look at them in parallel, the potential difference of the light bulbs will stay the same, but the current is shared between them. Yeah, so they're opposite to each other in series and parallel. So that's why the C for current, series, current stays the same. P for potential difference stays the same in parallel. Okay. So then the next thing is for resistance. So I put RI standing for resistance increases. Okay, so in series, the more resistors you put together, remember we said you sum up the resistance, so the resistance increases. So I'm going to put here resistance increases when adding more of them in series. On the flip side, in parallel, they don't increase, right? So I've got the 2 L's here. The 2 L's are like a cross. Yeah, so I split them into 2 L's to make a cross. Yeah, so no, current doesn't increase. Oh, sorry, resistance doesn't increase when you add multiple resistors in parallel. So resistance does not increase when adding more in parallel. Okay, so those are your key rules to remember as the differences between series circuits and parallel circuits. Current stays the same in series. Potential difference does in parallel. Total resistance in series increases the more you add. Total resistance in parallel doesn't increase when you add more resistors. Okay, cool. That's for series and parallel circuits. Okay. The next thing here, direct and alternating current. There's a very small bit in the spec that I wanted to cover the definition of each. Okay. So direct is direct. It goes from A to B. Okay. So there's no change in direction. It stays in one direction. Alternating current, alternating means to change. So alternating current is one that changes direction. That's the only difference. Okay. So sometimes a question that comes up, sometimes a 1 marker even, just what is the difference or what is the definition of one of those things. So direct current, I'll just highlight it, is in one direction. There we go. And then alternating current is current that changes direction. Okay, so that's the difference. Okay, and different examples of that. Direct current is from a battery. Alternating current is, say, from a plug socket in your house, which runs off alternating current. Okay. Then mains electricity. Okay, so we're near the end here for the guys on combined. So we've got maybe another, we've got about 10 minutes. I think we should get to the end about 12:20 for the guys in combined. So we're almost there. Mains electricity. The key thing you need to know here, one thing is how the pins in a plug work, a 3-pin plug. 3 pins for 3 wires, okay? And there is a way to remember these as well, okay? So I'm going to put this here. I'm going to go down to how you wire a plug. What is the way to remember how a plug is wired together? So there are 3 wires, blue, brown, and a striped wire. Yeah, usually striped for 2 colors. Okay. How do we know which one is which? So blue, I've covered the BL in blue because that is the wire that's in the bottom left of the plug. If I go back to the drawing, you can see here, blue is in the bottom left. It's connected at the bottom left. Okay, so bottom left is for the blue wire, and blue is the color of water, isn't it? Blue like water. So I'm going to say blue. The BL stands for bottom left, not bottom left, bottom left. And then it's blue like water. And if you, a bit of chemistry here, what is the pH of water? It's pH 7, but pH 7 is what we call neutral. So that is the neutral wire. Okay, so that's a way to remember it. So the blue wire is the neutral wire located in the bottom left of the plug. The next one I've got is the brown wire, and BR, like BL was bottom left, BR is bottom right, because it's connected in the bottom right of the plug. If I go up, yeah, there enough, there it is, live. Yeah, so how do we know it's the live wire? Because brown is the color of coffee. And what do you do? What do you feel like when you feel coffee? You drink coffee, it makes you feel alive. It makes you feel more alert, more awake. Yeah, so I'm going to put here brown like coffee. Because coffee makes you feel alive. So I'm going to put A and then live in capitals. Yeah, so coffee makes you feel alive. It's brown in color. That is the live wire. Okay. Where's the link for the cram revision session? I put it up earlier. Don't worry, I'll share it just before we go off for lunch again. Okay, so just bear with me. The last thing here is for the striped wire. So the striped wire, you can see at the top here, it's the third wire. It's striped, 2 colors. Yeah, usually green and yellow, which is what I've put there. How do we remember that is the earth wire? Because usually it's green and yellow, which is the color of the earth. Yeah. How do I know where it's located? Again, I've put all the locations in red, right? BL for bottom left, BR for bottom right, T for top. It's at the top of the plug. It's the top one there. And how do you remember the colors? So I've put the word striped in green and yellow, because green and yellow are the colors that you see on Earth, the sun, the grass. Yeah, green and yellow. It's colors of the earth, earthy colors. Green and yellow are colors of the earth. Yeah, so that's a way to remember the earth wire. So those are your 3 wires. You need to know where they're connected and how they work. Okay, so blue wire, the neutral wire, connects the circuit together. The live wire, the brown one, is the one where current flows through in normal operation. Yeah, so if you want your appliance to work, the current always flows through the live wire. The earth wire is there for if there is too much current in the circuit. Yeah, suddenly, when you get your current from your power supply at home, it can increase suddenly out of nowhere. There might be a surge of current coming from where you're getting your electricity from. That can cause too much current to flow through the circuit. The risk is that could give you an electric shock. You don't want that. Yeah. So what do we do to avoid that? It stops flowing through the live wire and flows through the earth wire. Where does it go? The word is the earth. It goes to the earth. It goes to the ground. Yeah, somewhere that it's insulated, so it doesn't go through your body and give you an electric shock. You don't want that. Okay. We then also have a fuse. A fuse helps to protect against that as well. The fuse will melt. If there's too much current flowing through the fuse will melt. The circuit will stop working. Okay, so that's another way to protect a person in using an appliance if there's an excess or surge of current in the circuit. Okay, so that always happens because here we're talking about the potential difference between us and the live wire. If there's too much current in the live wire and it reaches the person, there's a potential difference there. We have a potential difference of 0. We don't have current flowing through us, do we, or any sort of electricity. But the live wire obviously is running off the circuit in your home, which is 230 volts. Okay, 230 volts is what comes through your plug sockets anywhere in your house, and that becomes dangerous if it comes in contact with you. You're going to get an electric shock. So this is why we have the earth wire, we have the fuse, and then we also have what we say is double insulation. Double insulation is where a component has the earth wire, but also has an insulating cover like plastic casing to prevent you getting an electric shock. Yeah, so that's that. So I'm going to mention double insulation here briefly. Double insulation is where a component has an earth wire and an insulating casing. to protect from electrocution. Yeah, so it's all just to keep you safe. So that is what it does. It prevents you from having it by having two methods of preventing you from having an electric shock. Yeah. Okay. Correct. So that's the earth wire. Cool. So those are your wires in a circuit. That's that covered. Then we've got electrical power. So we saw power earlier, but that was for energy, right? We said the rate of energy transfer, energy over time, or work done over time. Here we have electrical power. So you can calculate the power in a circuit based off of the information in it. So there's two different ways you can do that. P equals IV, or power equals current times potential difference, or I squared R, current squared times the resistance. Okay. And I've made triangles for each. So you can go and cover up one. So here, I current equals power divided by potential difference. Or if I did here, I want the resistance equals power divided by current squared. Okay. So we use these because it depends on what they give you in the question. Okay. So in this question, if you go through both of them, you can see one question gives you power and potential difference. So if you have potential difference, you use this equation. Okay. The other question I have power and resistance, and they want us to find the current. So P, I, and R, that's this equation. Okay. So that's why you have two different equations depending on what you need to find. So you will go to your equation sheet in the exam and look at what do I know. So I always tick off. I'll always underline, okay, I have this and this, which is power and potential difference, and I want the current. So I need to look for those three letters in an equation. Okay. So labeling it like that in your answer is always a good way to help you. It is in the equation sheet, correct? Yeah, so that's what I'm talking through, how I would do it in an exam. Okay. Now, we talked about electrical power. Now we're talking about how energy is related to power, and that is the same equation as we saw before. Energy equals power over time. Yeah, so power in watts, energy in joules, and time in seconds. Okay, so that is the same type of equation. Here we're talking about electrical transfer of energy, aren't we? If we go back to the beginning, you can see these topics are all kind of related to each other. So you can see questions where we get some crossover because they might talk about energy transfer in, say, one of these appliances, and then talk about, say, what energy is transferred, what is the efficiency, things like that. It will all link together. Okay. So electrical energy transfer from the mains socket that the appliance is plugged into can be used for different things, right? So say for a vacuum, it's the motion, it's the motor that's used to suck up the dirt in your house. So that's kinetic energy as an output. For a kettle that you plug into the wall, it's electrical energy to thermal energy to heat up the water that you have your cup of tea with. So there are different types. Okay, so that is those two. Then one more equation. See, so several. How many was that? 1, 2, 3, 4, 5. Like five different equations. 6 if you include Q equals IT. Yeah, so many different ones. You'll get them in your equation sheet. The last one here is E equals QV, charge times potential difference. If you think earlier, I said potential difference is the energy transferred per unit charge by definition. Yeah, so potential difference V equals energy transfer per unit charge. And if you cover up V in this triangle, that's what it gives you, right? Energy over charge. Yeah, so it's just putting the definition into equation form. So we've seen these, it's just they're showing you multiple different ways. Again, all depending on what they give you in the question. So here, energy is in joules, and they've given you a potential difference and asked you to work out charge. So E, V, and Q. That is this equation. Yeah, so that's how you determine it. Look at what you need and what you have, and then go to your equation sheet and see which equation involves all those letters. That's the best way to do it. Okay, so that is that the last bit here. I think it's the last bit. Yes, it is. And then the last bit is triple. Cool. So we are dead on 12:20. I'm going slightly over, guys, but again, bear in mind, I will give you the full hour, and then we'll try and catch back a little bit of time after the break. But the last thing is the national grid, okay? And I want to go through this memory trick to teach you how to remember the order of the national grid and what everything does, okay? And that is, I don't know if you've seen it on our socials, maybe you've seen it on our TikTok before, but it's PopDoc, okay? PopDoc being the way to remember it. What does each thing do and what does each thing stand for? So the P, where we begin, where does our electricity come from? It comes from a power station. I'm going to zoom in here before my writing gets too big. P for power station. That's where our electricity is generated, where we can even go back earlier and say, where does that electricity come from? Fossil fuels, renewable energy, yeah, or your power station, wherever your energy resources. And that's being turned to electricity, which comes from the power station, okay? The next step is the up in pop. up, I've put as the letter up because it's a step up transformer. That's what this stands for, okay? And as it suggests, a step up. So you're going up in something, okay? The thing that's increasing is your potential difference, okay? Step up transformer. It increases your potential difference. And the key thing is you want to do that so that the current reduces, yeah? Because you want the current to decrease, because the more current there is, the warmer it gets. Remember the filament lamp? The increase in current, and then it started to warm up, and then the resistance went up. It's not efficient. You lose energy as heat. The lamp gets really hot. Same with the wires it goes to. So you want the wires to have as little heat loss as possible. And you do that by reducing the current, and that is done by increasing the potential difference. Exactly, Sammy. You're reducing energy loss. Okay. So I'm going to say here, the step up transformer increases the PD, so it reduces current. So I'll put that in brackets actually, because its main function is to increase the PD. So I'll take this out of the brackets. Increase the potential difference, so therefore it reduces the current. So therefore there is less heat loss and more efficient transmission. Yeah, transmission just means that the transfer or movement of electricity. More efficient transmission. Okay. And where is it transmitting through? It's those cables. You know, those pylons, you've probably seen them around, maybe near your house, maybe along main roads. You'll see it in fields. Those pylons that are like big pylons like this, they're all connected with wires above the ground. So it can transfer this high voltage, low current electricity very quickly all around the country. Okay. So that is what this is. The transmission cables or pylons. And that's this arrow. And then dock. So we've got the DO in dock, just like up for UP, DO for down. Yeah. So step down transformer is what DO is. I'll underline that. I'll underline this. A step down transformer. So the step up transformer increased the voltage, so it's super high, yeah, in the hundreds of thousands of volts. But our homes don't run off hundreds of thousands of volts. Like we said, our plug sockets are only 230, so we need to reduce it. It decreases the PD. Now, why does it do that? It's because we want the 230, we don't want hundreds of thousands, so it's safe for use in our homes and buildings. Exactly, Sammy, it's 230, correct. Yeah, so safe for use. That's why it decreases the PD, so we safely use it. And the last one, the C, that's you or I. Yeah, that's me right now with all the electrics around me. I'm the consumer. I'm using the electricity. Yeah, so homes and buildings. That is what the consumer uses at the end with the electricity, your 230 volts. Yeah. So that's how a national grid works, and that's what this explains in several different points. Okay, that's what this breaks down. And the last thing here, there is one more equation. Okay, because in the transformer, like we said, whether you're increasing or decreasing the potential difference, the power stays the same. And earlier we saw the equation for power, P equals IV. So the IV on the primary side equals the IV on the secondary. Okay, 2 coils. That's what it mentions here. There are 2 coils in a transformer. A primary coil before the current reaches the step-up transformer, and the secondary coil is the output afterwards. Okay, so there the power is the same, or is kept constant in a transformer. So you assuming a transformer is 100% efficient. Yeah, so it's all theoretical, because if you're assuming that it's fully efficient, there's no waste. The power entering the transformer is the same as the power leaving it. Okay, so that's what means we get this equation here. VI in the primary equals VI in the secondary coil. And yes, I was just going to mention at the bottom of these notes, for your consumer, the electricity is at 230 volts. And as you all have mentioned, it's 50 hertz. Yeah, they ask you as the frequency of your electricity in your house. 230 volts and 50 hertz, correct. Can you watch these videos afterwards? Absolutely you can. They will be on our YouTube. You have the link. When you reopen the link in your email, it will take you back to this and you can watch it again. So no problem. Yeah, if there's anything you need to revisit that I've said, do go back in it and have a look. No problem at all. Cool. That is everything for you guys that are in combined science. So thank you very much. It is 12:26. So we'll say It's an hour break for you guys. So if you can come back for, let's say, 1:25, I'll put the message in the chat. Before you go, 2 things I want to mention. I will send this link one more time because at the end of lunch, so at 1:25 it is, that will be the end of the entries for the spin the wheel competition at the end. Okay, so to join our cram classes, book your cram spot on here. So I'll go and show you again. It takes you, this link should take you to this page here. You just click on browse classes. So if I go to the page here, book your cram spot here, and it takes you to this section. Sign up, join whichever ones you like. If you want to join all of them, join for paper 2. And if you're successful with the spin the wheel, you will get all of it for free. Okay, so make sure you're signed up, and then you'll be in with a chance of spinning the wheel at the end of the session. So you have until the end of lunch, so 1:25, before entries will close. If you try and join after, it will not work. The wheel will already be generated, and I will be spinning it at the end of the session. Okay. You don't have to pay. You just join up for free. Join up on the paper 1 sessions, and you'll be in with a chance. Okay, but you have to do it before 1:25. But that's it, guys, for those doing combined. Thank you very much. Halfway there for you guys. I'll see you at 1:25. Triple, guys, we're going to carry on now. Bear with me. I think we'll need, I don't want to keep you too long, maybe 10 minutes. You'll have a 50-minute lunch. Hope that's okay. It's the suffering of being a triple science student. Yeah, but we'll be there soon. Cool. For paper 2, it's going to be sent to you as a link in your email. Okay, like I said, day before the class, you will get a link in your email, a secure link just for yourself to click on, and you'll join the session. Okay, and then yeah, thank you guys on combined. We're going to carry on with triple. Cool. So static electricity is what is introduced in triple. So the combined guys don't have to do this. We talked about electrostatic energy before. Obviously, that's all around this kind of thing. Static between charges. Okay. So the key things to remember here is how charges behave with each other. Opposite charges, so positive and negative, are your 2 charges. When they're opposite, so the different ones, they attract. When they're like charges, they repel. That's the key thing to remember. Okay, and all the charges, the way they work, give you the different applications. They're all based around this basis of attraction and repulsion between the 2 charges. Okay. How does charge transfer between objects? Is through friction or rubbing against 2 objects. So you can see, for example, here, the cloth and a rod. If you rub the cloth against the rod, it's the transfer of electrons between those 2 components. Okay. So a lot of the time when you are trying to explain how charge is transferred, it's due to the transfer of electrons. So that's the key point I want to underline. Okay. So electrons are transferred. Okay. So where they're transferred then determines the charge, isn't it? If you gain electrons, you become negatively charged. If you lose electrons, you're losing negative charge, so you become positively charged. So it's all about the movement of electrons. Questions on static electricity are hard to get full marks on. That's true. Yeah, it is true. They always make the triple bits a bit harder, but it's all about transferring electrons between objects to give them a charge. And then how do they behave with each other afterwards? Okay. So if one is positive and one is negative, they'll attract. If one is negative, the other is negative, they will repel. Okay. And then they talk about how a spark is formed. Yeah. So the dangers of static electricity. Like when it builds up, why would it jump to the air? Okay. So because ultimately objects want to be neutral. Yeah. So ourselves, for example, let me take an example of if you wear a jumper and you take off that jumper, sometimes you feel a spark or your hairs might stand on end. If you've got a bit of longer hair, your hair suddenly might stand on end. Now, why would that be? It's because when you take off the jumper is rubbing against your hair. That's that friction I was talking about. So when 2 objects rub against each other, there's a transfer of charge. So you might gain electrons and the jumper might lose electrons. Okay. Sometimes the jumper, as you're building it up, is already rubbing against your clothes, right? And even if you're walking around, it's rubbing everywhere against everything. It's built up charge over the day. So sometimes when you take it off, you do get a little, maybe like a snap noise, or even feel a little jump of charge, and you get a little shock in your body. Yeah, and that's because of the buildup of charge. Objects want to discharge to become neutral. So then it tries, by discharging, is trying to reach Earth. So when there's a gap, it has to jump through that gap. Air is also neutral. It can move electricity through there and then through yourself and into the Earth. Yeah. So that's a danger. You can, if it's too high, you get dangerous things such as lightning. Yeah. So lightning forms when clouds in the sky rub against each other because they're all sometimes moving at different speeds and different directions. They rub against each other. That friction causes a buildup of charge in the clouds. And the clouds want to lose that charge. They don't want to be charged. So they try and discharge by sending that charge to Earth in the form of lightning. You do not want to get hit by lightning. We all know that. Yeah, very, very unlikely, but also very risky. So mitigation or prevention of that happening, tall buildings have like metallic conductors on the end. So then the lightning gets attracted towards that and flows through that pole to Earth. Doesn't touch anyone, doesn't damage anything, goes straight down into the Earth and then becomes neutralized. Yeah, so that's where the electrons are transferred between the two clouds, causing them to become charged. And then you want to discharge by sending that to Earth. Okay. When you touch the electric dome, exactly. So what happens there is that the electrons from the dome are transferred to you, but then the dome is negatively charged, and so are you. So opposite charges repel. Like charges repel. So then your hair stands on end because you're negatively charged, and so is the dome. So then they're pushing away from each other. So that pushing force is represented in your hair because your hair is quite weak compared to obviously your body. It's not going to push your body away. It's not strong enough, but it will push your hairs to stand up on end. Yeah. So that's that. Cool. So wires in a plug, the PD difference between the live and the earth. So a large amount of current can pass through. Exactly that. Yeah, that's exactly what happens. And there's a jump or a spark if there is an air gap that causes that jump to happen. Yeah. So that's the potential difference between a live wire and an earth wire being 0 and us being 0. So you don't want any electricity going through you. So the electrons in your hair repel and stand each other on it. Exactly right. You got it. Yeah. So then when they you gain that charge, all of them are the same charge. So then they repel each other. And that's why it stands on end. And when it's neutral, there's no charge, your hair will stay flat. You don't have to name the name of the metal dome. It is called a Van de Graaff generator, but you don't need to mention it. Yeah, they'll put it in a question and say that. Cool. Then the last thing is electric fields. Okay. Electric fields. So like magnetic fields in paper 2, you have electric fields as well, which are an area in which an electric effect can be felt. Yes, you get an electrostatic force. Now, the lines show you the direction in which that is traveling. And the lines always travel. The key thing here, field lines travel from positive to negative. Yeah, so from positive towards negative is the direction of a field line. So it goes away from a positive charge towards a negative. So you see that here. With a positively charged sphere, you can see the arrows are all pointing outwards because it's going away from positive. But with an electron, say, all the field lines travel towards it because it's negatively charged. It goes towards negative. Okay. Then the field lines, depending on their distance, again, same as in magnetic fields. The closer they are, the stronger the electric field in this case. Okay, so that's what we've put here. A weak field, the lines are further apart. A strong field, the lines are closer together. And one more thing I wanted to mention in the notes here, I'll put a note at the end, is what it means by a uniform field. Yeah, so if we refer to a uniform field, is a field in which the lines are equally, what we call equidistant. Yeah? So equal distances apart. So that means if they're in equal distance, it means everywhere you look, the field strength is the same. Yeah, so meaning a constant field strength. Because if they were further apart in some areas, it's weaker. If it's closer together, it's stronger. You don't have that variation in a uniform field. It's all the same. So it's the same field strength. So it doesn't link to the magnetic topic, but the lines work in a similar fashion. That's what I was saying. The link is they act in the same way. Yeah. But one is to do with charge and one is to do with magnetic poles. So they won't be in the same question, but their behavior is the same. It's just with magnets, you talk about north and south. With electrostatic forces, you talk about positive and negative charge. That's the difference. Okay. And there we are. That is everything about static electricity. Yeah. So someone mentioned here, as I mentioned, take a look. The questions cover everything that you need to know, some calculations, some explanation, some circuits, some graphs. Yeah. Everything that we covered in this session. Take a chance to look at it. Obviously not now. Take a break. Yeah. Have your hour or 50 minutes now. Sorry, guys. I'll see you back at 1:25. Remember, sign up to the cram classes. Sorry. You sign up for paper 1, you'll be in the wheel for a chance to win paper 2. If not, then it's only £10. Yeah, it's not much. Day before the exam, we'll send you the link and you will have access to it for all the cram classes. that's it, guys. Leave it there. I'm gonna have a bit of lunch as well and a bit of a breather. Talking for 2 hours. It's been a good session. I think we've covered it pretty well. Sorry, we've gone slightly over, but not too bad. Enjoy it, guys. In terms of mark schemes, it's not on this workbook, but we do have some of these questions on our website. So take a look, and you can see if you can get the mark scheme there as well. Okay. And thank you very much. Hope you have a good lunch break. See you at 1:25, guys. Yeah, thank you very much. Enjoy. You don't mind going over, this is better. I'm a good teacher. Thank you. Much appreciated. Really appreciate that, guys. If there's, like you said, guys, as well, before I go off, if there's anything you want explaining again, I'll do my best in the time that we have. But yeah, 1:25, guys. Yeah, Jonas mentioned it. I'll drop a message as well. 1:25 p.m. We'll see you back here where we will start topic 3. Okay. See you later. Hello. Hello, welcome back. Halfway down, halfway to go. 2 more topics left. Hope everyone's doing well. Everyone having a good break. Time to catch their breath, get their minds rested, ready for the second round. Cool. So hopefully everyone has taken the chance now. We've now completed the wheel. It's now getting made with everyone that's signed up for the wheel at the end. So thank you very much to everyone that has joined. Look forward to seeing you in at least our paper one cram classes, and look forward to seeing you in others and one lucky winner later on. We'll find out later, Philip. It will be at the end of session 4. I'll do the spin live so we can see who won it. So don't worry, that'll be later on. Are we going to give mark schemes for the exam questions? So we're going to work on it, and we'll look to send that to you guys afterwards. So that's a work in progress. You can have that for reference, just so you can see how you've done on the questions. So yeah, fair enough. We'll take that on board and we'll look to get something sent if we can. Okay, without further ado, let's get into it. We are into topic number 3. Okay, so that is particle model of matter. This one, out of the 4 topics, is probably the smallest. So I'm hoping we can stick to time, maybe catch back to our slot of what was it, 2:15? We'll see how we get on. So first things first, density. Okay, so what is density? Density is the mass per unit volume of a substance. Okay, so if it's more dense, there's more mass in the volume. Okay, so in terms of, let's say, water or a metal block, the metal block is more dense because there's more matter in that amount of volume. Yeah, so it's more packed with particles, so it's more dense. Okay, so density is the mass per unit volume, or the amount of mass to the ratio of the amount of mass to the volume it occupies. Okay, the unit for it, as its mass over volume, you can see in the question here, in the equation, sorry. Mass, a standard unit, is kilograms, and the volume standard unit is meters cubed. So putting that together, kilograms divided by meters cubed is kilograms per meter cubed. Sometimes in questions, you will get 2 things where they ask you to convert either from grams, they may give you the mass in grams, so you need to convert to kilograms. So it's important to know to go from grams to kilograms, you divide by 1,000, or from kilograms to grams, you multiply by 1,000. The other one is centimeters to meters. Okay, so centimeters to meters, there are 100 centimeters in 1 meter. So you divide by 100 to go to meters, and times by 100 to go from meters to centimeters. So, but one thing I wanted to mention here is sometimes they could go that step further. And those of you that were in one of the Kahoot quizzes we did recently, I had a question converting from centimeters cubed to meters cubed. Okay, so I'm going to compare it here. So if we said 100 centimeters is the equivalent of 1 meter. But if I'm saying it's centimeters cubed, yeah, so if I said, let's say, so instead of 1 meter, it's 1 meter cubed. So I'll show the conversion as well, sorry, that we had for the top one. Nope. I want to rub it out, not highlight it. Sorry, bear with me. There we go. So remove that. In meters, we know that is to divide by 100 to go from centimeters to meters, and times by 100 to go from meters to centimeters. However, if we want 1 meter cubed, that means that these factors are now, and I'm going to make myself a bit more space. There'll be 3 cubed of that multiple. Okay, so what I mean by that is, before, to go from meters to centimeters was times by 100, but now actually from meters cubed to centimeters cubed is times by 100 cubed. In other words, 100 times 100 times 100. Okay, which is essentially times by 1 million. So 1 meter cubed is actually 1 million centimeters cubed. Okay, and then to go from centimeters cubed to back to meters cubed, you divide by 100 cubed, or in other words, divide by 1 million. Yeah, so that is the conversion that we use if you're going straight from centimeters cubed to meters cubed. Okay, so hopefully that makes sense. Sometimes, yeah, someone said 1 million. Nice, a few of you have. Cool, everyone's got it. Sorry, I was so focused on mentioning it here. Everyone's got it. Makes sense. Wicked. Yeah, so that sometimes it can catch people out. Make sure you've got everything in its standard units. I always mention that today, haven't I, in all the equations. Cool. The other thing I'm going to add here that we've said is density is the mass per unit volume of a substance. Yeah, if you want to put it in a definition. Okay. Cool. So that is for density. The next part of it, okay, that's for calculating it specifically more for material, mostly for solids. Yeah, we use this equation. The other thing as well, you can see in the mark scheme is not the mark scheme, the specification, the symbol for density. Yes, the Greek letter rho. It's like a slanted P. That's the letter in an equation for density. So based off of that, now we have the required practical for density. Specifically here, there's one for regular objects. So like I said, like a cube of a solid. And there's some for the an irregularly shaped object. Yeah, something like a rock or like a statue that's an unusual shape. Yeah. Do you have to remember the equation? No, you don't. It's given to you in the formula sheet, the equation sheet. It won't be in a question, but they'll say use the equation sheet to work out your answer. So that is something that you will need to do. Yeah. So yeah, that's something that you just need to know how to use it and work it out, but you don't need to remember it. It's in your formula sheet. If it's mass per unit volume, why does it vary depending on the arrangement of particles? Because the amount of particles in a particular volume depends on its arrangement, right? If the arrangement is that the particles are closer together, there's a lot more mass in that volume. If the particles are more spread out, the arrangement is different. There's less mass in that volume. So that's the difference. Okay. Cool. Okay. The next thing here is comparing these experiments. Okay. So like I said, for a regularly shaped object, like a ball or a cube, you can work out the volume by calculating the length of the sides and calculating the volume from that. Yeah. So for example, for a cube, it will be length times width times height. Yeah. And we said multiply that to find the volume. So if I had a cube here, like this, to find its volume, I'll say we need the height, we need the length and the width. So width and length. Yeah, so volume equals length times width times height. That's what we mean. Yeah, regularly shaped object. You can measure all of those. Depending on its size, you will then mention the apparatus. Remember, a ruler for larger objects, and if it's tiny or smaller, you'd use a vernier caliper. The scale is more accurate and can be in millimeters. Sometimes you have it in a digital vernier caliper as well to give you accurate measurements. Yeah. So then once you've got volume, you then need the mass, right? If you want to calculate density, density is mass over volume. So we've worked out volume. The other thing is mass. So you just put the object on a mass balance, record its mass. Yeah. So the only equipment you need for the regular one, a regular object, is a vernier caliper or something to measure the length, and then a mass balance. You then get those dimensions, work out the volume, do mass over volume. Then the last bit is the equation. Yeah. So that's it. So that is for a regular object. It's for an irregular object where it gets a bit more tricky. Now, here we have a memory trick. It's one of my favorite ones that I've seen Lean come up with. I always love the video. Those of you that haven't seen it, check it out on our TikTok. Lean's cool faces with some sunglasses on. Always love that one. So this one, the memory trick is me face. Okay, so we talk through all the different steps of what equipment we're using and how we're using it. Yeah, and that is what we step through to give us the 6 marks for how to measure the density of an irregularly shaped object. Okay, so first things first, M. Like we said, in the first question, we needed mass. Yeah, mass is the easiest thing to find because it's just an object. We can put it on a mass balance and we can record its mass. Okay, so that's the first thing we're going to do. So I'm going to put here, record the mass. So I'll say mass balance. And I say measure the mass of the object. Then the E stands for Eureka can. Yeah, so Eureka can is this can here. So it's like a beaker basically, but it has this open spout on the end. So you fill the Eureka can right up to that spout. Okay, and we're going to mention why in a second. So Eureka, because after the scientist found this out about how the displacement of water works, he said Eureka. It's a famous phrase. Yeah, so the can was named after that. So we call it a Eureka can. Okay, so that's another piece of apparatus we've mentioned. And remember, identify apparatus or equipment. The next thing I said already, is fill the Eureka can up to the spout. So that's what the F is for. So F for fill with water. and that's up to the spout. Yeah, so I'll put here up to the spout. Cool. So that's half of it. So 3 marks there already. The next one, now we've filled up the Eureka can up to that point. This is the point at which we add the object in now. Okay. So we go there, we add the object into the beaker. In this case, it says a key that we've got in the example. You put the key in, and as it goes in, it causes the water level to rise. And that's just enough for it to displace, what we say, displace the water. And so it rises and goes out through the spout until it levels out again. And all of that water is going to go into this measuring cylinder out of the spout. Yeah. So the next step here, we're simply going to say add the object into the Eureka can. So put that here. Add the object into the Eureka can. Okay. Now, after this, like I said, on the side, you're going to see that it fills up the measuring cylinder. So that is where you're collecting this displaced water. Yeah, so for the C, it's meant to remind you that we're using a cylinder, a measuring cylinder at that, and that is to collect the water that comes out of the spout. Okay, so I'm going to say for C, that is cylinder, and that is for a measuring cylinder that is used to collect the displaced water from the Eureka can. Okay, so as a result of that, from the measuring cylinder, you get that amount of water. That is your volume, isn't it? The amount that is displaced by indicates the volume of the object. So if I go back to the image, whatever is collected in here tells you what the volume of your object is. So now, the first step obviously gave you mass. The next 4 steps are all we needed to explain to make sure we got the volume. And now we're at the end, the E. We said we have mass, we have volume, so we can use the equation. So the last one is equation is used to calculate the density. Calculate density. And I'll put the equation here again. Rho, that Greek letter like P equals mass over volume. Yeah, and that's what you use. Use that and you get your value for density. So that is the difference between you doing it for a regularly shaped object and an irregularly shaped object. Yeah, regular shape, the first step is the same, mass balance. But the second step for volume is measure the dimensions and calculate the volume. Here, you can't do that because it's an irregularly shaped object. So this is where we use the Eureka can. That's the difference. Correct. Yeah, so yeah, so this practical is just called the density required practical, essentially. Yeah, it's just called the density required practical. But yeah, hopefully you find that memory trick useful. Like I said, if you want it ingrained in your mind, go to our TikTok, and that picture of Neen always sticks with me. It always helps me remember it. I never learned it before that. So yeah, really, really cool tip and a good way to break down a 6 marker. Can you say top pan balance? Yeah, you can. You can say top pan balance instead. That's fine. And then, sorry, you said, Minto, get the 4 marks. Sorry, will I get the 6 marks for what? Sorry, you've just said density. I think for, I guess with what I've said, yes, you can. Yeah. It's extremely helpful. Good to hear that. Thank you very much. Okay, so moving on then. So here we have states of matter next. Okay, so all the types of state of matter, what they look like, what their arrangement is like, and therefore this is where someone mentioned about why does the arrangement or does it affect the density, and I was saying it does. We see that here with states of matter. Yeah, so if we're looking at solids, the particles are tightly packed. It means they're condensed together. They don't move very much. They vibrate in fixed positions. Yeah, once they warm up, it will vibrate in its position. It won't move very far. And because of that, that means a lot of the particles are in a small space or in a small volume, so the density is high. Yeah, and that's what we've got here. Tightly packed, so then it's a high density. Whereas gas, on the other end of the spectrum, the particles are far apart, and therefore the density is low. Yeah, so the arrangement does affect the density. Okay, so the one thing here is knowing about, and just because sometimes it comes up, compressibility. That's why we've added it to the table. Solids are incompressible. Yeah, think about trying to squash it with your hands. Yeah, you can't really squash a metal block. You're not going to do it. Yeah. With a liquid, it's slightly compressible, right? It depends on what container it's in. If you like try if with a water bottle, if you close the lid and try and squash it, it does squash a bit, but not completely, right? But then with gas, it will compress very easily, highly compressible. You can squash a gas because really you'll do that and it will just change its arrangement. Okay. When will A-level content be updated to we're really working on that, Sarah. So yeah, no, good question. Trying to do what we can on that. Obviously, it's a lot of content. We're trying to perfect the GCSE stuff. I think we're getting there, and we're working on the A-levels in the background. So yeah, bear with us and keep an eye on our website, and we will be letting you all know once it's ready and good to go. So yeah, cool. So next thing, changes of state. Okay, so we know what the states are. Now, just a bit of an introduction to all the different types of state changes. So solid to liquid, the best example to use for this is water, right? So solid water, you put it in your freezer, it turns into ice, right? So you have solid ice. To get to water, it melts, right? So we have melting. And then from liquid to vapor, it's like putting it in your kettle, you're boiling it, and then it turns into vapor, gas. Going backwards, you have the steam like setting on your windows and turning into liquid. It's condensation, it's condensing. Yeah, it's like when you like breathe on a window because your breath's warm, you see that like mist. It's like that, right? When boiling water, when gas kind of cools down, it turns into a liquid. Then from liquid to a solid, so water to ice, like I said, you get that in your freezer, you freeze it. Okay, so the key things there is knowing where those points are. So melting and freezing happens at melting point, and boiling and condensation happens at boiling point. And the one here I've mentioned, okay, just so you guys know, solid to gas, where you go straight from a solid to gas, is called sublimation or subliming. Okay, so when a solid turns directly into a gas, it sublimates. So an example of where this happens is like on an ice cap in like the North Pole. Sometimes you see a glacier, and obviously that's a solid block of ice. But if you look at the surface of it, it's like there's like vapor coming straight off of it, and that's sublimation because it's just warming up and turning straight into vapor. And that's what sublimation is. That's the main example I see of solid going straight to vapor. What type of forces between the particles that cause them to be in that state? Oh, depending on the state. So especially with solids, you can have like they're all what we call intermolecular forces. Yeah, so the forces between the particles. It can depend on a solid. It can be electrostatic forces if there's charged particles and there's attraction between them. And then there's what we call but otherwise we call it intermolecular force between them. Is this topic common in paper 1? Yes, definitely. There will always be something on it, whether it's density, whether it's the practical, whether it's this states of matter stuff. It will be in there somewhere. But yeah, cool. Okay. The next bit here is about internal energy. So the internal energy of particles in a system. Okay, so it's the total amount of particles in a system. If you want to define it, it's the sum of the kinetic and potential energies within the system. Okay, because all particles are moving around, particularly in a gas, they move differently and they will have different positions. So remember, we talked at the very top of this in topic 1 in energy. Movement is kinetic energy, and position is gravitational potential energy. So the sum of those two together is what we call the internal energy, and that's where this equation comes from. Okay, total energy, internal energy equals kinetic plus potential energy. So it's the sum of the kinetic and potential energy stores within a system. What is it called when you go from gas to a solid? You could say desublimation. Obviously, it's not something we really see. It's not something they really ask you, which is why we don't include it. You don't have to think about it too much. Sublimation is the only one that may come up, but we don't really talk about that much about examples of going from gas to solid. Not that I've ever seen anyway. What do you mean by position? I don't get potential energy stores. Okay, so for example, it is a good question. So within a system, let's say within a container, in a box, some particles may be at the bottom of the box, some may be at the top. So depending on their height, they will be in a different position. So the higher the object is, the more potential energy it has, right? MGH we spoke about before at the start. Mass times gravity times height for gravitational potential energy. So the higher it is in the box, it's going to have a different potential energy to particles lower in the box. But the total is the sum of those potential and kinetic energies of all the particles put together. So that's what I mean by position. It's due to the height as well as where the object is. What is it called when it goes from a gas? Yes, that's what I was saying. We don't really need to know that. It doesn't really come up. People have mentioned desublimation. I guess you can call it that if you wanted to, but it's not really a thing that we see, and they won't ask you that. So the only one I've seen that could come up is sublimation, so solid to gas. Okay, so with the internal energy, we can see how that behavior changes depending on the type of state of the material. Okay, and you can see the lowest internal energy is in a solid because the positions are fixed, they're not changing, and the velocities of them aren't very high. They're not moving very much, right? They stay in position. So the total internal energy isn't very high. As you start to heat it, melt it, and then boil it, you will see the particles get further and further apart. They also move more. So therefore, their positions are changing more. So the potential energy stores and the kinetic energy stores increase. Okay. So that's the difference there. When you break the bonds of particles, their potential energy increases. Okay. That's the difference here. So gas has the highest internal energy and solids have the lowest. So the next thing here, latent heat. Okay, so latent heat is talking about the energy required to change the state of the substance. Okay, so specific heat capacity we saw earlier is the energy required to change the temperature of a substance, right? From of 1 kilogram by 1 degree C. Specific latent heat talks about the energy required to change 1 kilogram of the substance into a different state. Okay, so that's what we're going to say. We're going to highlight in this definition. If I go to the highlighter, so specific latent heat is the amount of energy required to change the state of 1 kilogram of substance. That's what it is. Yeah, there is no change in temperature when you change the state of a substance. That's the important thing to capture here as well. No change in temperature. And we're going to see this in what we call heating and cooling graphs in a second. But as you change state, the temperature doesn't change because the energy is being used to change the state instead. Okay. Whereas before, if it's changing the temperature, that's to do with specific heat capacity. When it's changing state, we talk about specific latent heat. Okay. So that's the difference. So I'm just going to mention that in the next box down here. Oh, actually, I don't need to. It's here. Yeah. So I'm going to highlight these points. So we said specific heat capacity is for temperature changes and specific latent heat is for state changes. That's the difference. Yeah, so that's why I'm just highlighting those. So that is for temperature change, specific latent heat is for state change. Okay. So we have different types of specific latent heat, which are combined by one equation. Okay. The equation is energy change is just mass times specific latent heat. Remember, for specific heat capacity, I'm just going to quickly note it on the side here. It was E equals mc delta theta, wasn't it? Where you had a change in temperature. But remember, I just said for a state change, there is no change in temperature, which is why this isn't here. So instead of talking about specific heat capacity L, we change that to C. We change that to an L. Sorry, yeah, and that is specific latent heat. So that's the difference. There is no temperature in this equation. So you've seen this equation before. It's just without the temperature change. So because of that, the units are different, aren't they? If you think about this here, again, another triangle. Yeah, I talked about a lot of these with equations. Try and use them for people. Some people find them quite useful. If I want to find the unit for specific latent heat, I can cover up the L here. And the equation is L equals E divided by M. Yeah, so remember E is measured in joules for energy and mass is measured in kilograms. So E divided by M, joules divided by kilogram, joules per kilogram. And that is where the unit for specific latent heat comes from. Okay. Sometimes they do ask. How do gases have a high internal energy? Good question. So as I mentioned earlier, when you heat it up, remember total internal energy is the sum of the kinetic energy, which is the movement of particles, and the position of the particles is potential energy. In a gas, they're moving around and have a lot more freedom to move than they do when they're a solid. There's nowhere it can move, right? Look at it, it can't even go anywhere. Yeah, whereas a gas has a lot of range of movement, so its kinetic energy is really high. And because that happens, they change positions. Their positions will change as well. So there's a lot of change in position, so that changes as well. So that increases both kinetic energy and potential energy. You add those together, that's your total internal energy. So that's why it increases. Cool. So that's for latent heat, okay? And with that, there are two types, again, because of the state changes. So, for example, for solid and liquid, so when you're talking about either freezing or melting, you talk about specific latent heat of fusion. Yeah, so that's what we've underlined here. Specific latent heat of fusion is for the state change of solid to liquid or liquid to solid. When you go from liquid to gas or gas to liquid, we call it latent heat of vaporization. Yeah, so if you want to remember it, the easy way is to think of vaporization as the one with vapor, and then fusion is the other one. So fusion is solid and liquid. Okay, so they fuse into a solid, but they vaporize into a gas. Okay, so vaporization is for liquid and gas. Fusion is for solid and liquid. So here is an example of a question, and it asks us for the specific latent heat. Okay, so they've given us a specific latent heat, and they're asking us to calculate the energy. Yeah, so it says 7,800. If I underline it, as I would, if I did a question, this is exactly what I'd do. I underline the key values. So mass 7,800 grams, and it says it melts at 0 degrees. So we know that's a constant temperature. And it says it's then heated to 100 degrees until it turns into steam. And to calculate this in standard form, the energy. Okay, so we want to calculate energy. We're given the mass, and we've also told you in the question specific latent heat of fusion, specific latent heat of vaporization. So the first question is for a block of ice from solid to liquid. So solid to liquid, remember I said that's for fusion. So we're going to have to use this value first of all, 334,000. And the equation was E equals ml, which I've put here. So we know M is the 7,800 grams. Is it in its standard unit? No, it's in grams. So we need to convert it. So that's 7.8 kilograms. So that's what we've done here. And then now you can use the equation 7.8 times your 334,000, and that gives you 2,605,000. In the question, it asks to calculate it in standard form and three significant figures, which is why this is now rounded to three significant figures. So that's 2, 6, and then the 0 rounds up to a 1, and you put it in standard form. So that's times 10 to the power of 6. And that's where you get the answer from. Okay. The second question, underline it in green, is for liquid to gas. Yeah. So then liquid to gas, that's to do with vaporization. So we use the 2.26 times 10 to the 6 this time, but we keep the same mass of 7.8. It's still the same amount of substance. Okay. So that's the difference. Could you quickly write down the prefixes for physics, please? Sorry, I'm not sure what you mean by that. But I can try and help if you mention what you mean. Apologies. I meant to remember the specific heat capacity of water. No, you don't have to. It's like I put it earlier in the booklet. It's like 4186. So as you say, rounds to 4,200. But they should give you the value in the question. Yeah, or they're going to ask you to calculate it. So in which case you use all the other values: the energy, the mass, and the change in temperature. But you don't have to. Okay. Are you referring to how much would A and B be worth? Someone's mentioned. So 1 mark for a conversion, 1 mark for the equation, 1 mark for the answer. It can be 3 marks or an additional mark if they don't give you the unit, 1 mark for the unit. Yeah. Sometimes in a question like this, it could even be another mark for, it says number of significant figures. So if they ask you specifically for that, that is an exclusive separate mark. So sometimes if you give just this answer, you will lose a mark or you'll miss out on a mark because you haven't given it to the significant figures or decimal places they've asked you for. Yeah. So I would say each of these I would say 4 marks is probably right for this. Yeah. Unit conversion, equation, answer, and unit as the max you can get for it. So I'm going to say somewhere between about 4 marks. Okay. So that is specific latent heat. Now, heating and cooling graphs. This is what I was talking about. Yeah. So here we can talk about how the energy changes in a substance. Yeah. So depending on when it is heated or melted, what is happening to the energy stores within a substance? Okay. And what is causing that to happen? Okay. So as I was saying, when you increase the temperature, that is to do with specific heat capacity. Okay. So I'm going to say along the slanted lines, that's where you're seeing a temperature change, right? The temperature is going up. So in the solid section, that is to do with specific heat capacity. So SHC. Yeah. Then in the second section where it's melting now, it's a flat line. The temperature isn't changing, right? And where did we say temperature doesn't change? We said specific latent heat. So I'm going to put SLH for specific latent heat. Okay. Then it's now changed into a liquid. The temperature is now rising. We're into the territory of using specific heat capacity to calculate energy transfer. And then we reach boiling point. It's now starting to boil. The temperature doesn't change. So the energy is being used to change the state of the substance. So we're looking at specific latent heat. Again, in this case, latent heat of vaporization. Okay. So what I'd call it as L with a subscript V for vaporization. Here it's L with a subscript of F for fusion. Okay. And then lastly, in a gas, the temperature is rising. So we're back to specific heat capacity again. Okay. Now, at each of these 2 stages where the state is changing, why is the energy or why is the temperature not changing? It's because the energy is not being used to change the temperature. The energy is being used to break the bonds in the substance. Yeah. So from a solid, bonds are breaking to turn into a liquid. And from a liquid, bonds are then breaking when boiling to turn into a gas. Okay. So here in those 2 sections, I'm going to say energy used to break bonds. That's why the temperature doesn't change. Okay, it's a question that they sometimes ask. The energy is used to break the bonds so the particles are free to move, changing state. Exactly. So because the energy is used to break bonds, it won't increase the temperature. Exactly. Yeah. The LF and the LV, so latent heat of fusion and latent heat of vaporization. Okay. So that's on a heating graph. You can see the temperature is rising. Yeah. Anywhere it's rising, the graph goes up. Anywhere the state is changing, the temperature remains constant because the energy is being used to break bonds. Okay. Okay. So that is for a heating graph. On a cooling graph now. Okay. So the graph is going the other way, right? Usually a gas is at a higher temperature and then you start to cool it down. Okay. So here we're going to see how the energy is used in this case. So again, as before, anywhere there's a temperature change is related to specific heat capacity, right? SHC. And then same for the liquid and same for the solid. Yeah, so when the temperature is changing in the same state, you think about specific heat capacity. But when there's a state change, we're looking at specific latent heat, SLH. Yeah, again, it's condensing between gas and a liquid. We look at latent heat of vaporization. And then for a solid to liquid or liquid to solid, it's the latent heat of fusion here. Okay, so LF. And in this case, when we're condensing or when we're freezing, the gas is now becoming a liquid or the liquid is then becoming a solid. The energy is now being used to make bonds instead of break bonds. Remember earlier when we're heating it, we're breaking the bonds. But here, we're now using the energy to form bonds. Okay, so the temperature doesn't decrease, stays the same because the energy is then being forced into making bonds. Okay, so I'm going to put here bonds. Making bonds is the trend for these two sections, freezing and melting. No, not freezing and melting, freezing and condensing. Sorry, making bonds. Okay, so you can see in the heating graph, it was about breaking bonds, and now in cooling graphs, it's about making bonds. Okay, cool. So again, I'm going to highlight the key point, which I mentioned in both of these. It's just underneath here in these paragraphs. I'm going to say that the energy is being used. So the energy removed is being used to change the state of the substance and make bonds. Yeah, so that's the key point. That's what we're referring to here. Yeah, whereas earlier, if I can find the point, it says for heating graphs, the energy, where have I got it? Sorry. Here we are. So temperature does not increase in this phase because the energy goes into breaking the bonds. Yeah, so that's what it is for heating, and then for cooling, energy removed is being used to change the state and make bonds. Okay, so that's the difference between the two, and that's specific latent heat. Okay, fine. So I think we're almost at the end here. Look at that. Yeah, we're almost there. How's the time? Yeah, just at 2 o'clock. Okay, just a few more minutes, and then what we'll do is, if I finish, let's say, I never thought I'd say this in one of the sessions. If I finish this before the 2:15, we'll look at a question just before we finish off. Yeah, so particle motions in gases. Okay, so gases consist of large number of particles, but they're all spread out, aren't they? Yeah, and the key thing here is that they have all moved with a constant and random motion. Yeah, so gases, they move really, really randomly. You don't know where the particles are going. They're just free flow. They can do whatever they want. Yeah, they have total freedom. Now, what happens as you change the conditions around those particles? So imagine these particles in this container. So this purple rim here is like a container. So all these boxes are bouncing around in this container, moving wherever they want. If we increase the temperature, what do we think that does? Increasing the temperature increases the energy store within the particles, yeah, particularly the kinetic energy store. So that's going to cause them to gain kinetic energy. Kinetic energy is half mv squared, so the speed increases. Okay, so that's where we get the speed of the molecules increasing. So as the temperature rises, the speed of the molecules rise. And if the volume is fixed, like we said, in this fixed container, what is that going to mean? These particles moving randomly and moving faster, look at them. They're all going to collide anyway, aren't they, in directions eventually. And if they're moving faster, those collisions are going to be greater, more frequent, and stronger. So those forces between each other causes the pressure to increase. Okay, so an increase in temperature leads to faster moving particles because they have greater kinetic energy. So then their collisions are more frequent, and the kinetic energy, the pressure therefore increases. Yeah. So I'll say that here. Therefore, more collisions and pressure increases. Yeah. So here, then the next thing we're talking about is how pressure works with these particles. Yeah, so going the other way. So let's say we had a container and the pressure inside it increases. That we increase by having more particles in there. Again, pressure is dictated by the number of collisions and the frequency of the collisions and the strength of them. Yeah, so if there's more particles, they're more likely to collide, aren't they? Less space to move around in, more chance of bumping into each other. Yeah, it's like being in let's see, what can we compare? Being in a shed and being in a hall. You're less likely to bump into people in a hall. You're more likely to bump into people in a shed when you're in a tight space. Yeah, same thing with particles. So therefore, if you're looking at particles in relation to pressure, the less particles there are, the lower the pressure. Okay. And then, yes, someone's mentioned it. If you're looking at volume, that's like saying you make the space smaller, then you're increasing the pressure. Yeah. So there's two ways of doing it. You either have more particles in the space, that increases the pressure, or you reduce the volume. So you're just increasing the likelihood of collision. That's the aim, right? So gases increase in pressure if they're either in a smaller volume or there's more matter in that space, more particles in that area. Okay. So that's how pressure works. Now, the key thing here as well is the units for pressure. Pressure is measured in pascals or atmospheres. Okay, so pascals is, in other words, newtons per meter squared. Yeah, because pressure is at the force per unit area of something. Okay, atmospheres is used on a higher level, so it's like 10 to the 5 Pascal, something like that. It's a lot bigger. It's a bigger scale in terms of amount. In terms of are they inversely proportional? It depends on the conditions. Okay, and this is where we're going to see here the pressure temperature relationship depends here that are directly proportional at a fixed volume. Okay, so this is when the container is fixed. So I'm going to say here fixed volume. So if the volume is fixed, the container is the same size. If the temperature is higher, like we said, the particles are going to move faster, then that means they're going to be more likely to collide. And also when they collide, the forces between those collisions will be greater. Both of those things together leads to an increase in pressure. So therefore, the higher the temperature increases the pressure. So lower temperature, the pressure would be less. And that's the relationship. Okay. And the explanation is exactly what I've said. It's just here in the notes as well. If we heat a gas up, they gain kinetic energy, move at faster speeds, collide more frequently and more forcefully. Okay, and the key factor, as I've said, fixed volume. I guess I didn't need to write it because it's here as well. At a constant volume, increase in temperature increases the pressure. Yeah. So they are directly proportional in this state. Okay. And that brings us to the end. Yeah, so we've reached the end of this topic. It's the shortest one of the lot. What I wanted to do, let's see, have we got time? Yeah, we got time. Let's have a look at some questions. So what does the equation say? Which equation are you referring to? Sorry, strawberry cheesecake. Yeah, so PV equals constant. So that's a pressure volume relationship, right? So I haven't gone through that. That is, and Le Chatelier's, that's a different, that's chemistry. We don't cover Le Chatelier's in this. Yeah, so I'm not going to mention that now. The only equation I've referred to is pressure is, density is mass over volume. That's the one we need to know. Okay, exactly. Cool. So let's take a look at a couple of questions then. Yeah, so I've got some here. We've got a little bit of time. Let's go through a couple. So here it says, write down the equation linking density, mass, and volume. I guess that's what people are answering. Sorry, I was yapping away. You are right. So you can either write it in symbol form because they've given the symbols, or in letter form. Yeah, so I'm going to go, or in word form, sorry. I'm going to go with symbols. I'm going to save my writing. So the mass of the apple was 85 grams. I'm going to underline that. The density of the apple was 0.68 grams per centimeter cubed. Calculate the volume of the apple. And it says, give your answer in centimeters cubed. So they've told you the unit to give it in. So if I look at everything, 85 grams, that's for mass. Yeah, so again, I'll note down what I know. The density of the apple they've given us, that's rho, Greek letter for P, 0.68 grams per centimeter cubed. So mass is in grams, the density contains grams as well. So I don't actually need to change it because they also want us to keep the volume in centimeters cubed. So I don't need to change any units here. Volume is what they want us to find. So they see in this example, we've given the equation above, we've written it, rho equals mass over volume, but we want to find volume. So we need to swap density and volume over. Volume actually equals mass over density. So we just substitute in the numbers, 85 divided by 0.68. Does anyone have a calculator on them? I'm going to do it myself as well. So that is 85 divided by 0.68. That is 125 exactly. Yeah, so 125. And obviously they've given the unit, but I'll put it here, 1, 2, 5. And that's 3 marks. Yeah. 1 for the conversion. No, sorry, the equation being rearranged. 1 for the numbers subbed in and 1 for the answer. 3 marks. Okay. So yeah, exactly. Some people said it easy 3 marks, right? So that's all good. Cool. Will there release a revision guide online? If obviously you're signed up to this, you should have got it in your email. The revision guide should be there. That's why I was saying you can have them, refer to them, print them out, and then annotate them. Obviously, you can revisit this stream after, and you can annotate along with it if you like. Okay, so here we go. I'm not going to write this one out, but I'm just going to talk through it before we finish off. Keys are usually made from metal. The diagram below shows a metal key. Describe a method to determine the density of a metal key that the metal key is made from. You should include the measuring instruments you would use. Use the physics equation sheet. And it's 4 marks. It's only 4 marks. But exactly, someone shouted it out already. Fantastic. Me face. Me face is what we want to use. Yeah, that is it. Means face with the shades. That is what comes in clutch here. Yeah, those are the points you need to make. And if there's a 6 marks, I would still follow me face. Yeah, I would still follow the same thing. So sometimes it's given us 4 marks, sometimes it's 6. Yeah, so sometimes they will say 6 marks. So follow those same steps. Just make sure you cover all of those points, and you'll be good. Okay. Another 4 marker. Describe the difference between solid and gas states in terms of the arrangement and the movement of their particles. Okay, so here you can refer to it says the arrangement and movement. So it's 4 marks. So 2 marks for arrangement and 2 marks for movement. Okay. So, and it's between solid and gas, right? So you just need to state each. So solid, fixed position. Someone's just mentioned it. Nice, Sammy. Gas, freedom of motion, random motion, loads of space, etc. Yeah. So the arrangement far apart. And that's 2 marks. Then the movement. So gas moves freely and solid vibrates in fixed positions. And there we go. 2 marks and 2 marks. Yeah, so 4 marks looks scary when you look at the number of lines they leave. It's like daunting to go, oh, I need to fill the space. You don't need to think about filling the space. You just need to cover the points. If there's 4 marks, make 4 points. That's it. There aren't answers available yet, but we're looking at putting it together so that you can have a set of answers to try against these questions. So you can just see how you did and make sure you understand, if you didn't get it right, where to get your answers from and how to get the marks for it. I didn't sign up personally and just found the video. How can I still access the guide? Sign up on our, you can sign up still. It's not too late. So I'll send the link again. Give me 1 second. You can still sign up here. So give me 1 second. If I go to the right page, there we go. Great. So this is the link I'm sending is for the one for now for these boot camps. Yeah. So click on that link. You can sign up to our bootcamp right now, and that will give you the guide. You'll get an email with the guides sent to you for what we're doing right now. Okay. For paper 2s, you will need to sign up for paper 2s. They're £10 each. If you are in the session earlier, you are in the spin the wheel competition. Sign up to our cram classes as well. The paper ones are free again, but £10 for the paper 2s. Cool. Okay, so it's 2:10. I'm going to leave it there. So I think we've gone over a couple of times. It's only right I balance it out a bit and we can go a little bit earlier. Yeah, it's 2:10. What I can say is I'll answer some people's questions here. But if anyone's happy to go, we'll come back at 2:25, if that's okay with everyone. If you can be back at 2:25. And then we will resume from there into topic 4, which is atomic structure. Yeah, obviously it's not as short as this. It will be longer, but we should reach the hour, and then obviously we'll do the spin the wheel at the end. So see you at 2:25. Someone's asked, can these booklets be the only form of revision? It's part of your revision. So someone's the TK, you literally just said what I was going to say. It's part of your revision. Yeah. So these revision guides are helping you to form a set of notes. Yeah. Something that you can read back on. Then you need to do like some memory recall. Make sure you remember those notes. What's the best way of doing that? Trying some questions, which is why I've got some questions in the workbooks, in the revision guide, sorry. But that's not all you can do. Yeah. You need to do papers. You need to now start testing yourself in terms of exam technique, doing it to time. That's a big thing. Yeah. Some people can answer questions, but maybe you're taking too much time on it. Also, doing it with notes. Sometimes if you've learned the notes enough, then you go, okay, let me try the questions without notes. And then you see how you're doing. Then you really realize which bits you're weak on. Then cycle through the process, read notes on those bits that you're weak on, then go back again to try paper questions and do a whole paper again. Yeah, and then you should get to the point of keeping to do papers again and again and again. Will there be Kahoot quizzes soon? Yes, we'll look to resume them probably soon. Not as soon as they usually are. I think we'll see how we're getting on, but I think it will be after Easter at the moment. But we'll see. Keep your eyes peeled, and we'll look to see if we do some more in the Easter break. What do you what do you do if you have a teacher that doesn't get up from their seat and sits on their phone? I mean, this is what we're trying to help with as well. I mean, I don't know teachers who does that, but it's fine. This is what we're trying to help with. Yeah, we're trying to help you revise these things as well. So we've gone through 3 of the 4 topics, 1 more hour, and we've gone through the whole of paper 1. That should be your basis to start going, okay, let me try some questions. Yeah, from there, you then do this cyclical process. Like I said, try questions, see where you went wrong, read the notes, try again. Yeah, and then you get into the point where you're just doing papers over and over again. Okay, so Jonas dropped it in the chat. You've got a last chance for anyone that hasn't joined yet. It's the last few minutes to spin the wheel, to join the spin the wheel that we're going to do at the end, and that will be the end of joining it. And I will be doing the actual wheel spin at the end of this session. Okay. Can I do this question? Yeah, we got 2 minutes. Why not? Let's have a look. So the air contained water that froze at 0 degrees. The change in internal energy of the water as it froze was 0.7 kilojoules. The specific latent heat of fusion was 330 kilojoules per kilogram. Calculate the mass of ice produced. Use the equation sheet. Okay, so what have they given us? They've given us a change in energy. So E at 0.70 kilojoules, not 0.07. I've said 70, 07. I don't know how I've done that. 0.70 kilojoules. Yeah. Then the second thing they've given us is latent heat of fusion. So that's LF, which is 330 kilojoules per kilogram. Now, we can choose to change the units. Really, because both of the things are in kilojoules, we don't need to, because we're going to use the equation to work out the mass. But for completion's sake, I'm going to say, let's go to standard units. Kilojoules to joules multiplied by 1,000. So this would actually be 700 joules per kilogram. Not joules per kilogram, just joules for the energy, and then times the latent heat by 1,000 to give us 330,000 joules per kilogram. Okay, so we have those. We want to find the mass, calculate the mass. Okay, so the equation that links them, you can go to your formula sheet, you can go up to our notes. E equals ml, right? That is what we mentioned up here. Let me get there. There we are. Yeah, so the equation E equals ml. So that's what I'm using. And then I'm saying mass times latent heat, but we want the mass. So I'm going to rearrange the equation. So that means mass equals E over latent heat, which are 700 joules. Let me write that properly. 700 joules divided by 330,000 joules per kilogram. Okay, and if you put that in your calculator, I'm going to do it on mine just now. So 700 divided by 330,000, that is 0.002 kilograms. There we are. That's your answer. And that's what I put in the answer box. 3 marks. So you don't, like I said, you don't, in this case, you don't have to multiply by 1,000. The reason I did it is to get it into standard units. Yeah, I said the standard units for energy is joules. They've given kilojoules. And the standard unit for specific latent heat is joules per kilogram, not kilojoules per kilogram. But because both of them are the same here, you could have actually done 0.7 divided by 330 and you would have got the same answer. But I was just showing you turning it into its standard units. That's all. Cool. Okay, we'll leave it there. It's 1/4 past. If seeing as we've gone there, I'll say I'll give you the break now. Okay, so join at 2:30. I'll drop the message in the chat. See you in 15 minutes for our last hour. Okay, so I'm going to drop that in the chat now. So see you at 2:30. Otherwise, I'll answer some questions if I missed them. If you're sending them over the break, I'll quickly look at them at the start. But just to see these two, does potential energy decrease or increase if a particle is cooled? If it's cooled, its potential energy decreases. Okay, because then the bonds are being formed again, it decreases. As you heat it, the potential energy increases. So if an FRO member spins the wheel, you wouldn't have signed up now, right? You're an FRO classes member, so you didn't sign up. What is the next hour on? It's on atomic structure, topic 4, actually. So that's going to be next. So things like history of the atom, radiation, things like that. And then there's a little bit of triple at the end on nuclear fission and fusion. Why do you multiply if the units are kilojoules? Because kilojoules to joules is like kilograms to grams. You multiply by 1,000. There are 1,000 joules in 1 kilojoule. So that's why you times. Okay, see you in a bit, guys. Thank you very much. See you at 2:30. Hello, guys. We made it. The final hour, the last bit. Yeah, we got to topics 1, 2, and 3. We've just got topic 4 left, which is on atomic structure. How's everyone feeling? Are you feeling ready? Who's feeling tired? I don't blame you if you are, but if you are, bear with me for the last hour. We're almost there, and then a bit of fun at the end with the wheel spin, just something to enjoy. Yeah, so just a little bit of fun at the end. But we're almost there. Okay, last push. So atomic structure. This is stuff on obviously structure of the atom. A little bit of crossover with chemistry here for the one and only time, really. Some of this stuff at the beginning is kind of similar to chemistry. Then we get into things that are then separate, things about radiation, radioactivity, that are specifically for physics, and then a little bit of triple at the end. So I'm going to need 5 minutes at the end of this to go through the guys bits that the guys doing triple are doing, and then we'll get into the spin the wheel and the closing out of this session for today. There won't be a quiz tonight, Frozen. Apologies. After today, I'm pretty knackered after this. I'm probably not today, but there may be one later. Keep your eyes peeled later, maybe in the week for another quiz later on. Cool. Okay. Could you explain the calculations near the end? I always get it wrong. If you can be specific, maybe atomic structure calculating. Okay, we'll see if there's a question at the end. I'll see if I get time. Hopefully I do. Are you doing chemistry? I'm not, Sarah, but we do have it in our on one of our next sessions later in the week with Neen. I will show this later on. So I'll show you at the end what's coming up next. It was in our break screens as well, but don't worry, I'll show you at the end what's coming up next. Okay, so let's go. First things first, the structure of an atom. Okay, so atoms are basically the smallest particle that we have in the universe, and it's made up of what we call subatomic particles within them. Okay, every element has atoms that make them up, and within an element there are the subatomic particles: a proton, a neutron, and an electron. Okay, now you can see the neutrons and protons are in the nucleus of an atom, so which is at the center, and then you can see the electrons orbit in what we call shells or energy levels around them. Okay, we need to know their relative charge. So a proton has a charge of +1, electron of -1, and neutron sounds neutral, so it's 0. Okay, and what we see is with electrons in those energy levels or electron shells, when it absorbs radiation or energy, it becomes excited, so it gains energy and moves up an energy level. So another electron shell up. The opposite way, if it releases energy or emits energy, it goes down an energy level. Okay, so those are the comparisons there. Another key thing to remember, we had it in the quiz the other day. It was in a chemistry quiz, I believe. But again, also in physics, you need to know this radius of an atom and the radius of a nucleus. So you compare the two. The radius of an atom is 1 × 10⁻10 meters. So a nanometer is 1 × 10⁻9. This is 0.1 nanometers essentially. Think about how small that is. You will definitely not be able to see it with the naked eye. And a radius of the nucleus is obviously even smaller than that. It's another 10,000 times smaller at 1 × 10⁻14 meters. So really, really tiny bits we're talking about. The nucleus is positively charged. Yes, correct. Cool. Okay. And that's because it contains the protons. The neutrons are neutral, so the overall charge of the nucleus is positive. But then you have the electrons outside. So usually there's an equal number of protons and electrons in an atom, so its charge is 0. So neutral atoms are neutral and have no overall charge is the overall reflection here. So we then get into mass number, atomic number, and isotopes. Okay, so when you look at elements in the periodic table, you see they have a number at the top and a number at the bottom. Okay, the number at the top is the mass number. The mass number refers to basically the number of protons and neutrons that sit in the nucleus. So the number of protons and neutrons in the nucleus is the mass number, and the bottom number is just the atomic number, so just the number of protons. That's the difference. Okay, so if you wanted to find the number of neutrons, you have to subtract the top and the bottom numbers. So subtract the mass number from the atomic number. So I'm just going to add that note here. So if you want to find the mass number, no, not the mass number, the neutron number, that would equal the mass number minus the atomic number. So that's how you obtain the number of neutrons. So if I go back up to that example of carbon 12, just here, so if I take this here, the number of neutrons, as you can see, the mass number 12 minus the atomic number 6 to give you 6 neutrons. And then usually for an atom, as it's a neutral atom, the atomic number gives you the number of protons. So then the number of electrons should be equal to that. Okay. And that's what you see here for all of these. Okay. And what we're showing here is that an element is one type of atom. Okay. An isotope is an atoms of an element with the same number of protons or the same atomic number, but a different number of neutrons. And this is where we see these three. See, they're all carbon because they all have an atomic number of 6. So they have the same atomic number, they are the same element, but they have a different number of neutrons. Yeah, so we do that calculation for neutrons again for these three. For the neutrons one here, it says 12 minus 6. Yeah, because the mass number is 12. 12 minus 6, that's 6 protons, 6 neutrons here. For carbon 13, the mass number is 13 this time. So you do 13 minus the atomic number, which is 6. Now the number of neutrons are 7. And then for carbon 14, it's 14 minus 6, and the number of neutrons is 8. So you can see for carbon, they're isotopes because they have the same number of protons and electrons, making them the same element, but they each have different number of neutrons. So they're all different elements. Okay. Not different elements, sorry, they're all different isotopes, okay, because they have a different number of neutrons. Okay, so the next bit here is the structure of an atom, yeah, and the history of an atom. How did the structure get formed? So what I want to ask you guys, who can remember the memory trick for this? I think I saw someone mention it in the chat earlier. Sorry if I missed it. Obviously, we weren't on the topic at the time. Can anyone remember what the memory trick is for this? Have you guys seen the picture of it? Fair enough, DJ Rock Band Club. We call it DJ Red Blood Cell, but DJ RBC, exactly, guys. Yeah. So DJ RBC is what I've put underneath here, and we're going to talk through each of those. Yeah. So the section covers it in the notes in more detail. I'm going through the summary of it as a memory trick for those of you that don't know it. So this is for each of the scientists, right? So that discovered something about the structure of the atom. The first person being Dalton, John Dalton. Yeah. So the D is for Dalton. What did Dalton discover? He initially discovered atoms were essentially spheres, right? So that is the discovery first. So atoms were spheres. Then we have the J. So the next scientist was J.J. Thomson. Yeah, so J.J. Thomson. And J.J. Thomson discovered the plum pudding model. Yeah, so we talk about the plum pudding model as a sphere of positive charge, and the little raisins are like the dots of negative charge around it. He didn't know they were electrons at the time. They're just known as dots of negative charge. So plum pudding model. After that, the R came for Rutherford. Thanks, Sammy. Well done, guys. So R is for Rutherford. Ernest Rutherford. I think it was actually Rutherford and Ernest Marsden, two scientists together, but Rutherford is credited with it. So Rutherford is the person who discovered what the structure of the nucleus was. He didn't necessarily call it the nucleus as such. I guess that came a bit later as well, but Rutherford was responsible for identifying there is like a nucleus with a positive charge, and then around it there was lots of space, lots of free space around it. Okay, so that's what we're going to put here. So I'm going to say a dense positive nucleus with surrounding empty space. So now after Rutherford, we've now got the nucleus. He did the alpha scattering model. Exactly, said everybody. He's the one that did it. Yeah, so he fired alpha particles at a gold foil, and he discovered that a lot of them passed straight through, which suggested the empty space that I'm referring to here. And then he found that some bounced straight back or got deflected completely. That suggests that because alpha is positively charged, the center of the atom is also positively charged, hence the positive nucleus that he discovered as well. Exactly. Yeah. So the next thing is after Rutherford was Niels Bohr. Okay. Niels Bohr, he found out about the electron shells in an atom. Yeah. So Rutherford found out about the nucleus. Then he said there was space around it. But what he didn't find out, which Bohr did, was that there were electron shells, which are the electrons that orbit the nucleus, which we saw at the beginning there. And then lastly, the last scientist was Chadwick. Yeah, so Chadwick discovered the neutrons. Yeah, so we discovered positive charge in the center and then electron shells around it. But what we didn't identify were the neutral particles, the neutrons that also sat in the nucleus. And that is what Chadwick had discovered, James Chadwick. So I'm going to put neutrons in the nucleus. That's the last one here. So there you go, DJ RBC, DJ Red Blood Cell, DJ Rock Band Club, however you want to remember it. Those are the different scientists in chronological order, yeah? So in order of time. So Dalton was first, then J.J. Thomson, then Rutherford, then Bohr, then lastly Chadwick discovering the neutrons, which gave us the structure of the atom we know today, what we call the nuclear model. Yeah. Okay, cool, moving on. So the next thing we've got is radioactive decay and nuclear radiation, the large chunk of this topic, okay? So here, we're going to say what the different types of radiation are, and then also their key properties, okay? So I've got a couple of little memory points here that I've tried to put together, but we'll revisit the table a little bit to just chat a bit more about them. So alpha, what is alpha? So firstly, we've got that it is a positively charged helium nucleus, okay? So the P is for positive charge. Plus 2 to be exact, because there's 2 protons, 2 neutrons in a helium nucleus. The H standing for helium nucleus. Then the L I've put in purple because it's a specific property about alpha that it is the least penetrating. Yeah, and I'm going to get into penetrating power in a bit. Penetrating means to pass through things. Yeah, so it's the least penetrating. That's what it tells us. And then on the end of alpha, you can see I haven't written A quite right. I've actually written A as the symbol alpha, the alpha symbol. Yeah, that's the symbol for alpha radiation. So that's a bit about alpha. Beta, you can see here, the B also doesn't look quite like a B. It's the symbol for beta radiation. And then I've highlighted the E here because we're identifying that it is a high-speed electron. Yes, I'll put high-speed electron, which we know an electron has a charge or relative charge of -1. Okay, so that is for beta. And now lastly, for gamma, we know that gamma, I've given an M because the L we had in alpha was the least penetrating. Gamma is the most penetrating. Yeah, so beta is like the steady eddy in the middle. It's moderate. Yeah, it's kind of it's more penetrating than alpha, but not as penetrating as gamma. So it's in between. Yeah, and gamma is an EM wave, correct? An electromagnetic wave. Yeah, so we go into the table here, comparing them. Here you go. I've got the charges here: positive +2 for alpha, negative -1 for the high-speed electron. That is beta, and then you can see here in the table, as you've mentioned there, just know that gamma is an electromagnetic wave and it has no charge, 0 charge. Okay, it is not a particle, it is a wave, so it has no mass either. Okay, so then we compared the penetrating power. You can see it increases as you go from alpha to gamma, alpha being the least and gamma being the most penetrating. And also, what is it stopped by? So alpha can be stopped by a few centimeters of air or just even paper or our skin, so it won't pass through our skin. But beta can travel a bit further, it's stopped by like an aluminium foil. And then gamma can travel the furthest, it can definitely pass through us. It can be stopped by thick concrete or thick lead. Okay. The opposite way around is the ionizing power. So the ionizing power is about how ionizing it is. Ionizing something means to turn an atom into an ion. You knock electrons off of it to turn it into an ion. Alpha is the most ionizing and gamma is the least ionizing. So it goes the other way around. Yes, you can see ionizing goes alpha being the highest, whereas penetrating is alpha is the lowest. So what does this tell us? Alpha is the least dangerous outside our body because it can't penetrate. But once it's in the body, alpha is the most dangerous because it can ionize atoms and cells in our bodies, and it can cause mutations of cells and damaging cells, ultimately leading to cancer. So that's a big risk. Okay, so gamma is most dangerous in our bodies. Sorry, alpha is most dangerous in our bodies, but the least dangerous outside of it. So that is what this table summarizes, and this is what this shows. And then we've got a couple of uses here. Okay, so some key uses. Alpha radiation is used for smoke detectors. Okay, why is that useful? So if you think of a smoke detector on your ceiling, in normal operation, alpha particles are passing through the to the detector within the actual alarm. But when smoke comes up, smoke passes through that gap. Alpha can't penetrate the smoke, and then the alarm sets off because you're not detecting anything. That's a danger. The alarm sets off. Okay. So that is what it's used for. Exactly. Smoke blocks it. You've mentioned it. Nice. So then beta particles are used for a couple of things. They're used for thickness measurement, as you can see here, because if you have a beta emitter and a beta detector, you need it to pass through, but you want it to vary how much passes through depending on the thickness. So alpha isn't useful because alpha would just be stopped at all times. So you can't detect anything. Gamma, you'll detect everything. It will always pass through unless it's super thick, but you're not making it like that. You're looking for thin sheets, whether it's metal sheets or paper. So gamma will always pass through. So that's not useful either. Beta is in the middle ground. It will vary depending on the thickness. So it's the best use for this. Okay. Similarly, it can be used for detecting leaks or cracks in pipes for the same reasons. It can pass through the crack, but it will be stopped by the pipe. So where you detect the radiation from within the pipe, you know there's a leak there. If you can't detect it, there's no radiation. Alpha will never be detected. Gamma will always be detected. So those two aren't useful. So it's having that middle ground of penetrating power. And then lastly, gamma rays are used as medical tracers. What do I mean by that? So medical tracer is something like you ingest a pill containing some gamma radiation, okay? And the doctors will use a detector from outside to detect how the gamma is moving within your body, okay? And that's useful because gamma can penetrate very easily, so we'll always detect it outside the body. Alpha and beta maybe not, and also alpha, remember I said, is very dangerous in your body, so you don't want to have it. You don't want to have that. And beta is more ionizing. Gamma is the least ionizing, so it's also not as harmful in your body. So it has a dual purpose. Very easily detectable outside, but it's better than beta because it's not as ionizing inside your body, so it's less harm to you. So those are just some of the uses and comparing the different types there. It is half-life. Half-lives is the plural, by the way, and we're going to get into that in a second. So the next thing that we see is decay. And in terms of that, the equations of decay of different types of radiation. Okay. So starting with alpha decay, you're losing a helium nucleus. So you're losing something with a mass number of 4 and an atomic number of 2. That's what you'll see at the end of the equation on the right-hand side. If you're losing a beta particle, this is the tricky one. People find the most tricky. 0 minus 1. Okay. So minus 1 is the atomic number. The reason is, remember, it's an electron. There's no protons in it. It's just simply an electron. So it's like a proton is missing. So it's minus 1. And the mass number is 0. There's no protons or electrons. Okay. So there we see beta being emitted. And a key thing we notice as a result of that, a proton turns into a neutron. Okay. That's what happens. So that is for beta decay. And then for gamma, it's an EM wave. So it has no mass number, no atomic number, 0, 0. You're just emitting energy, essentially, in the form of an EM wave. What is a positron? A positron is basically a positively charged electron. It's the opposite of an electron. Not a proton, it's slightly different. But you don't need to know that for this exactly right now. Okay, that's in A level. So if you're doing A level, something for you to look at. Okay, here we go. An example of how to work out a decay equation. This can come up in your exams. So here they're saying a radium nucleus decays into polonium and releases alpha radiation. So you can see alpha is on the right-hand side. It's alpha because it's 4 and 2. 2 protons, 2 neutrons, a positively charged helium nucleus. So what is the polonium's mass number and atomic number going to be? And this is simply just maths, okay? We want to equate the total mass number on the left should equal the total mass number on the right. So you can see in green here, I've got 219 on the left equals x, let's call this x, plus 4. So then we rearrange, so x equals 219 minus 4, so this has to be 215. So then these two added together give us our 219. Yeah. Similarly, on the bottom, it's 86 equals x plus 2. So if I said this was x plus 2, we resolve that, x equals 84. So we have 215 and 84, so that both the numbers on the left add up to give the total on the right. That's all that's happening. Yeah, so that's for an alpha decay. Looking at a beta decay, you can see here the key point I've said during beta decay. One thing to remember is that the number of protons change because a proton turns into a neutron. Yeah, the protons change because a neutron turns into a proton, doesn't it? Apologies for that. That's my mistake. A neutron changes into a proton. Why is that? I'll explain it by the equation. Okay, you'll see how it changes by the numbers. So let's take a carbon-14 nucleus here, and you can see it's going from into nitrogen and a beta decay. Yeah, so a beta particle is emitted. In other words, 0 minus 1. But we do the same thing. It's the maths that we want to work out. So let's look at the top. 14. The mass number is 14. So what plus 0, x plus 0 equals 14. So then x is going to be the same value. X still stays at 14. Yeah, so that's 14 there. The mass number is the same. However, at the bottom, 6 equals x plus minus 1. X plus minus 1. Yeah, that's the same as x minus 1. So you rearrange. So if I said this is equal to x minus 1, that's what I'm going to put there. Sorry, I'll do it in permanent writing. Equals x minus 1. Yeah, so you rearrange, x will equal 6 plus 1. So you get a mass number, atomic number of 7. So you can see here, the atomic number has gone up. So we've gained a proton. Okay, so but the mass number stayed the same. It's still 14. Remember, that refers to the number of protons and neutrons. So if I subtracted it, 14 minus 7 means that here there are 7 neutrons, where before there were 8. So we've lost a neutron, but we've gained a proton. So in beta decay, a neutron turns into a proton. That is what happens. Okay, so that's the thing to remember. Okay, so that's for beta. And then, like we said, for gamma, it's just gamma radiation that's given off. So you can see the nucleus before and after stays the same. 23892 uranium stays as 23892 uranium, but it becomes stable by emitting gamma radiation. Okay, every time something is emitting radiation, it is so that the nucleus becomes stable. Okay, whether it changes as a result or not depends on the type of radiation. Gamma, it never changes. It just releases the radiation and now becomes stable. Is beta radiation given off as electrons? Exactly, because beta radiation is a high-speed electron. So you're emitting an electron, essentially. Yeah, that's correct. And then, okay, people are talking about half-life. I'm going to come on to that, so bear with me. I'm just coming on to that now, I believe. There we go. Okay, so with decay, this type of decay, yeah, alpha, beta, gamma, it's random. Yeah, so it's not always fixed that, oh, every second, every time, every click I'm making, for radiation is being given off. No, it's not a regular heartbeat. It's very random. The comparison we always give is this dice analogy. Rolling a pair of dice, what are the chances you're going to get a 6? Yeah, it's technically a fair dice is 1 in 6, but it doesn't always work out. It's random, right? Sometimes you can get 6 twice in a row. You could be lucky. Yeah, if you're playing like snakes and ladders, you want the highest number possible. You get a 6 twice. You could roll it. You're lucky. Yeah, doesn't always work out that it's just you'll get 1, 2, 3, 4, 5, 6, then 1 again. It doesn't work out like that. Yeah, so very, very random. So the process is random, and what we're saying is the radiation is given off, like I said, to stabilize the nucleus. So it's undecayed. It then decays, gives off this radiation, and then becomes stable. So here you can see which ones decay are also very random. So we have all these blue undecayed nuclei. One decays here, another one decays somewhere else. It's not like where it decays, another one will decay right next to it. Which ones decay are also completely random. Okay. So then we look at the time it takes for those nuclei to decay, and this is what we get into what we call the half-life. I've seen a couple of definitions in the chat there, and you are right. It's the time it takes. There's 2 ways we can define this. The time taken for what we call the activity to halve, which someone has mentioned. What is the activity? I knew someone was going to ask that. The activity is the number of decays per second. Okay, so the number of nuclei decayed per second is the activity. Okay, the unit for it is either decays per second or becquerels. The scientists call becquerels. The unit is capital B small q. Yeah, it's the number of decays per second. So the activity, the time it takes for the activity to halve will be, for example, say the activity of the substance is 1,000 becquerels to start with, or 1,000 decays per second. The time it takes for it to halve to become 500 decays per second is a half-life. Okay, that's the difference. One thing people also mistake is that therefore, oh, the half-life is every 500 becquerels, so then the next one will be at 0. No, it's the time it takes for that number to halve. So you're always halving it. Okay, so the time it takes for it to go from 1,000 to 500 will be the same time it takes to go from 500 to 250. Okay, the time it takes for the activity to halve. You can also mention that the half-life is the time it takes for the count rate to halve. Yeah, so the count rate, if you guys have used it, there is what we call a GM tube, a Geiger-Müller tube. At school, you may have done the experiment, or your teacher may have done it in front of you. It clicks every time you hear radiation, or there's radiation around, and it clicks every decay. So you count the number of clicks per minute, let's say, and you get a count rate, the number of clicks per minute. Yeah, and then the time it takes for that count rate to halve. So let's say we started at 20 clicks per minute. It'll be the time for it to reach 10 clicks per minute. Yeah, so it's the same thing. It's about halving that number. Okay. The other way you can look at it is in terms of the nuclei. Yeah, so let's see our 32 nuclei to start with aren't decayed. The time it takes to go to 16 is the half-life. Yeah, to go from 32 to 16. And then our next half-life will be from half of 16, so 16 to 8. Yeah, and that's the second half-life. So you can see here how many half-lives we have. Initially, 32 undecayed, none are decayed. The time it takes for half of them to decay, so 32 divided by 2 is 16. That's your first half-life. The second half-life is for then the undecayed to decay by half again. So if we go from 16 to 8, yes, we halve again. This is the one thing these are the wrong way around. I just want to swap these numbers for you in the notes. Something you might want to change here. This is 8 and this is 24 are now decayed. And then lastly here, from 8 undecayed, it halves again to 4 that are decayed, leaving 28 in total decayed and only 4 undecayed. Okay. So it's the time it takes for the count rate to halve, the activity to halve, or the number of nuclei to decay by half. Okay, so that's what we were referring to. Half being the key term there. Okay, so every time it halves, that's one half-life. So let's say the half-life of something, they may give you a time frame. Let's say the half-life was 2 years. It would take 2 years to do this, but it will also take 2 years to do this, even though it's only dropping by 8 instead of 16. It's the time for it to halve. Yes, it's just half the value. It would take 2 years to do that, and then again another 2 years to decay the last 4. Yeah, for example. So it's that same value every time. You didn't see, I don't know, YouTube XP is a bit weird, but thank you. It's good that you're explaining it. It's good that you understand it. Yeah, using that to even explaining it to someone else, we find is a great revision technique, because if you can tell someone else, that means you know. The fact that you can teach or tell somebody else that you know it or what it is and explain it to them, then you understand. Yeah, that shows your understanding. Here are a couple of examples, literally talking through what we just mentioned about activity and how it decreases. So 2 half-lives will be times half and times half. From 200 times half twice, you get to 50. Yeah, so for example, if you're looking at it on a graph, yeah, and on the y-axis, here I've chosen activity. It can be the same, whether it's count rate, activity, or number of nuclei. The graph looks the same in terms of its curve like this, what we call an exponential decay. And then you look at finding the half-life in the same way. So here, initial value is the one when t equals 0, time is 0. So here we have an activity of 8. So one half-life is the time it takes to get from 8 to half of 8, which is 4. So I've drawn a line from 4 to the graph and then gone vertically down to determine the half-life. So the half-life, therefore, is at 3 days. Yeah, the unit says days, so 3 days for a half-life. Let's look at the next one, just to make sure it makes sense. So the next half-life will be from 4 halving to 2. So I'll go to activity of 2, go across the graph, and lo and behold, we're at 6. Yeah, so that's the half-life. It's not quite right. I'll draw the curve a bit bigger. There you go. It touches there at 6. So another 3 days have passed, and we reached our second half-life. Yeah, and then lastly, 1, it should go all the way across to 9 as it goes another 3 days, and that'll be our third half-life. So the time per half-life is always the same. Yeah, so that's what they want you to do on the graph. And sometimes they ask you that. They'll give you a graph and say, determine the half-life. And you would need to show these lines on your graph to show how you worked it out. So basically, I'm doing this FRL classes today, so that's what I do as well. What is the count rate? Jathona said, the count rate is, like I said, with the Geiger-Müller tube. So I don't know if you've had it at school. It's basically like a tube that clicks every time there's radiation present. And you count the number of clicks per minute, hence count rate, the number of counts in an amount of time. Yeah, so count rate. So for example, there was 20 counts a minute. The time taken for the count rate to half would be the time for it to go from 20 clicks per minute to 10 clicks per minute. It's literally how many clicks you hear. You count them. That's the count rate. Is radioactive decay the time taken for unstable nuclei to half? That's the half-life. It's another definition, right? So I said it's the time taken for the number of nuclei to decay by half. It's the time taken for the activity to half, or it's the time taken for the count rate of radiation to half. Yes, so any of those three. And no problem. That's fine. Good question. Is the count rate experiment required practical? No, it's not. It's not. It is something that triple students need to know, though. You'll see at the end, to do with background radiation, not for combined. It's not a required practical. Okay, so that is decay. Now we're on the last bit here of radioactive contamination and irradiation. Okay, so here we have 2 different types of things. What is the difference between contamination and irradiation? Okay, so contamination is direct contact. That's what I underlined here. I'm going to highlight it. So if you're contaminated by radiation, it means you're in direct contact with it. It touches your tissue of your skin. Okay, so you can occur by touching it, inhaling it, or eating it, ingesting it. Yeah, those are your ways. You're in direct contact with the radiation. Okay. To avoid that, how are you avoiding touching it? Wearing protective clothing, wearing protective goggles so it doesn't go in your eyes, wearing a mask so it doesn't go in your mouth, wearing gloves so it doesn't go on your hands. Yeah, so that is preventing against contamination. So you see these guys in what we call them hazmat suits. That's what they're wearing. If they're around radiation, look at them covered head to toe. There's not a part of their body that can be exposed. Even where you can see their eyes, it's like a plastic thing on the cover on the mask. Yeah, so you're not none of your body is exposed to prevent you being contaminated by it. Okay. You wouldn't wear lead gloves because it's super heavy. Yeah, so you just need something that's going to prevent the radiation suitably. Yeah, the point is that you're going to reduce it as much as possible while still doing the job. Obviously, lead would be ideal, but lead is too heavy. You're not going to wear lead gloves. There may be some lead in the material though, but not completely lead. So that is contamination. Okay, irradiation is being exposed to the radiation, but it doesn't become radioactive. Okay, so if a person is exposed, but the object themselves doesn't become radioactive. Okay, so an example of that is where you're near some sort of radioactive isotope, but it doesn't actually reach you. Yeah, so it says here, I'll highlight it. When a person is near radioactive isotope, the radiation given off reaches them. Yeah, so when it reaches you by non-contact, essentially. Yeah, so not direct contact. That is when you are irradiated by radiation. Contamination is when you touch it directly, ingest it directly. Irradiation is when it's kind of the waves reach you, right? So like gamma rays, they reach you without touching you. They can reach you from a distance. Yes, that's irradiation. So to prevent irradiation, you want to stop that radiation from spreading. So you need to contain it. So this is where we'd have like a box, in specifically like a thick concrete or a thick lead box. And that's what we would do. So what we call a lead line box. Yeah. And then keeping them in separate rooms. Yes. You're trying to distance yourself from it. That's to prevent irradiation. Contamination is preventing you touching it at all, reaching your skin directly. Irradiation is distancing yourself from it. Okay. And here again, we've got the table comparing the risk of contamination compared to irradiation. Okay. So contamination is when it's directly touching you. That's alpha, right? High ionizing. We don't want it to touch you because it can ionize you. But in terms of irradiation, it's where they can reach you from afar. So gamma is the most risky for irradiation. Okay, so that's the difference. Okay, and that leads us to the end of the content for combined science, guys. Yeah. Internal contamination. How would you prevent that? Like I said, you don't ingest it in the first place. Once you've ingested it, you will be contaminated. So you're trying to prevent yourself ingesting it, putting it in your mouth, eating it, or breathing it in. So you wear a mask. Yeah. The safety suit is called a hazmat suit. Yeah, you don't need to know it for the exam. It's just called a hazmat suit. But you don't need to know it. I'm just telling you, just for your reference, you can say it. So it's like a hazardous materials suit, hazmat for short. Yeah, so it's a hyphen between it. Hazardous materials. Okay, bear with me for like 5 minutes combined, guys. I'm just going to finish the triple stuff. And then once we finish that, we will go into the closing bits and spinning the wheel, and I'll call it a day there. Okay, so just bear with me combined, guys, just for 2-3 minutes. There's a couple of triple bits to cover. First of that being background radiation. Okay, what is background radiation? It's radiation naturally in the environment. So like I said with the clicking of the Geiger-Müller tube, usually put it near a radioactive source and you hear the clicks. But you'll also hear it if you hold it in the air, naturally in the environment around us. Yeah, if I just hold it in front of me, there will be some clicks around me. Very, very little, but there will be a small amount of clicks because there's radiation naturally in the air. Okay, so when you're using the Geiger-Müller tube to calculate the count rate of a substance, you need to do the following. You need to work out the background count rate and subtract it from whatever you've measured on the substance, because obviously that's including the background around you. Yeah, so that is the difference. You take the measured count rate, subtract the background count rate, and it gives you the actual corrected count rate for the radioactive substance. Okay, so that's one thing you need to know. The other thing here is knowing the conversion for radiation dosage. Okay, so what kind of dose of radiation you receive. Dose of radiation is measured in sieverts, SV for short. Okay, and then we need to do the conversion of that, because sometimes more often than not, you're exposed to a small amount of it. Okay, so usually it's given to you in millisieverts. So just like millimeters to meters, millisieverts to sieverts works the same way. So from millisieverts to sieverts, you divide by 1,000, and then from sieverts to millisieverts, you multiply by 1,000. So in questions, they could ask you, you just need to be careful that you convert to the right unit, depending on the question. Okay, so that's cool. That's about dosage and background radiation. So you can see here, literally mentioning it here, conversion of millisieverts to sieverts, and then where background radiation is found. Yeah, so background radiation, you can see natural sources in the environment, radon gas, cosmic rays, and then man-made radiation, so nuclear weapons and stuff. And then you have the uses and risks of radiation. So here you go into, we talked about some uses with the combined guys, but for triple, you need to know a couple more in a little bit more detail. Okay, things such as radiotherapy for cancer treatment. Okay, so that is when you fire gamma rays at a tumor in your body. Say it's in my arm. They fire those gamma rays directly at my tumor area. However, the risk of that is that a tumor doesn't exist as just unhealthy or damaged cells alone. There are your healthy cells there as well. So gamma rays kill the damaged cells, but they also kill any healthy cells around it as well. And that's the risk. Okay. The risk there is that the damaged cells, the healthy cells also get killed, and then it leads to cancer anyway, yeah, or further development of your cancer. So it's a risky process, but it's one of the treatments that people try and use to heal or recover from cancer. And then the other one I mentioned is about medical tracers. I did mention it briefly with the guys in the combined topic, but the thing you add on here that's important is that you want a source with a short half-life. Yeah, so we said gamma is the correct thing to use as a medical tracer because it can be detected outside the body. Yeah. However, it is still ionizing. It might be low, but it still does ionize. So there is a risk. You don't want it in your body for too long. So you want something with a short half-life. That means it's going to decay quickly, so it won't be in your body for very long. Yeah, so something with a half-life of a few hours or days at most, not something with half-life of years, so it's in your body for ages. Then you're more at risk of being causing mutation of cells and ionization. You don't want that. Yeah, so the difference here is that you have a limited exposure to it. So we say a short half-life, so it decays quickly. That's the key thing here. Yeah, that's what they add in terms of why you use it as a medical tracer. It's always something you should explain. Okay, and the last piece, okay, on this topic as a whole, for triple guys, is nuclear fission and nuclear fusion. What is the difference? So fusion, fuse, join things together. You fuse things together. That's joining of atoms to make a heavier element. Yeah. Fission is the opposite. It's when you split an atom and it breaks into smaller atoms. Okay, so we'll talk about fission first. It's when a neutron is fired at a radioactive nucleus, usually uranium. Yeah, uranium is usually the option for that. You fire the neutron at it and it splits into smaller atoms. So you can see here, you've got your uranium nucleus. You fire the neutron at it. It causes the uranium nucleus to split into what we call daughter nuclei. So smaller ones. This is, for example, barium and krypton, which are two smaller elements. And then more neutrons are released as a result. Those neutrons then go on to hit other uranium nuclei, and we get what we call a chain reaction. Okay, so that's what we need to know. We need to be able to explain that. So a neutron fires into a uranium nucleus, it splits into daughter nuclei, releasing neutrons that go on to split other uranium nuclei, repeating the process in a chain reaction. The important thing is every fission reaction releases loads of energy. Okay, it releases gamma radiation and a lot of energy. So massive amounts of energy being released per reaction, you get loads of buildup. This is what leads back to when we talked about nuclear power in the first topic. Nuclear power is based off of this. A reactor undergoing a fission reaction in the reactor, releasing loads of energy. Doesn't this use the principle of E equals mc squared? It does somewhat. You don't need to know it for GCSE. It does come up more in A level. Yeah, but you don't need to mention it now. So it's not something to know right now. But here we go. It just explains a bit more about further fission reactions. You can see this is known as a chain reaction. And I'm saying there's a nuclear reactor, and we talk about controlling the chain reaction in a reactor. I don't know if you guys have heard of it, but there's something called the Chernobyl disaster, where a nuclear power station, the power plant, exploded because there was so much energy in the nuclear fission reaction, it caused an explosion. It wasn't controlled. So you need ways of controlling it. Things such as what we call a boron rod. You lower it in, it absorbs neutrons. The less neutrons there are, the less fission reactions take place, as an example. Okay, so what we say is we need to control the reaction to make sure there's not an explosion. Otherwise, people are using it for things such as nuclear weapons, which isn't good. Yeah, we don't want World War III. Well, I'm not going to get into that. Anyway, we don't want weapons of nuclear power because their results can be catastrophic. Okay. So lastly, we said fusion is the opposite of fission. I've said that here. Yeah, so opposite of nuclear fission is fusion, when you join atoms together. But to get them to join together, you need massive amounts of energy and pressure to force atoms together. Why is that? Because remember, in a nucleus of each of the atoms, they're positively charged. So they're going to try and repel each other. You need to overcome that repulsion. And that is a really strong repulsion once you get really close together. And that's going to need loads of energy and in the form of temperature and pressure to make that happen. Okay. So here you can say, this is where someone mentioned about E equals mc squared. This is where you see it, but that is in A level, not now. Okay. So for example, the process at its basic level is hydrogen atoms fuse to form helium atoms. And as a result of that, you release energy. Okay. So it's a lot of energy to put into it to make it happen, but massive amounts of energy is given off. Really, if they could get it right, the amount of energy for fusion apparently is greater than fission. So really, it's a really good thing. Also, on top of that, you're using hydrogen, which is so easily available in the atmosphere. Uranium is available, but you're getting radioactive waste as a result, which isn't good. Yeah. So fusion actually releases more energy, but it's just being able to create the conditions for it long term is difficult, because the only place it naturally happens is the sun. Think about the size of the sun; it's massive, right? And it's really so hot, so high energy. So it's hard to recreate those conditions on a large scale. And yeah, this is the last point we mentioned. Energy released from fusion is much greater than the energy released from fission. Yeah. And that's it. I think that's the end of it. Nuclear fission and fusion covered there. There we go. Excuse me. Sorry. That is the end of it. Okay. We've reached the end of the topic. Well done, guys. You don't. Do you need to know the control rods are boron? They don't specify going into that detail for you. Again, that is an A level. You just need to know that you need to control reactions. Otherwise, it can go out of control in the chain reaction, leading to an explosion because of the large amount created. You just need to know it needs to be controlled. Yeah. Nice. Glad you guys found it useful. Thank you so much for today. Really good interaction. Really good questions from you guys. It made it much easier for me and much faster for me. The time absolutely flew every hour. I was like, how's this time gone? So really grateful to you guys. Thank you for joining. I hope you found it useful. We've got about 10 minutes left. So here we are. Just dropped it in the chat. I was just going to mention, guys, I'll talk about what's happening next. So I'll start with our schedule. So obviously you've had physics with me now. The next thing is going to be with Neen. So I will go to 1 second. Let me share my screen. There we go. So you can see the schedule. We've had me now today, Sunday, the 29th of March, we're almost in April, guys. Time's flying. Yeah, so we've had that. The next session will be on the last day of March, so on Tuesday, day after tomorrow. Neen will be doing biology paper 1. Okay. So please join us for that. Same schedule, starting at 10, as you can see, trying to get to 3:30. So where we are now. So we're just slightly early, which is great. And then Neen again on Thursday, the 2nd of April. So this Thursday, going to cover chemistry paper 1. Okay. And that'll be paper 1's completely done. Then moving into the week after for paper 2, biology, on the 7th of April. Then again, Thursday for chemistry on the 9th. And then lastly, I'll be back with you again for physics on the 12th of April. Okay. So if you have FRL classes, obviously you already have access to it. If you don't, and you enjoyed this and you found it useful, please do sign up. And we look forward to seeing you there. Or if you win by spinning the wheel, which we're about to do any second now. Okay, so let's take a look. I'm going to spin the wheel. Here we go. So we've got everyone's names in here. I'm going to click it to spin. Good luck. Let's see who is going to be our winner. Remember, if you win this, you'll get access to paper 2s of all the boot camps next the week after next, and also all the cram class paper 2s as well. Yeah, all of you that are on here are signed up to paper 1's cram classes, so thank you for that. But you get the chance here to win the paper 2s for free as well. Drum roll. Thank you. Exactly. Yeah, so let's have a spin. Here we go. Who's going to be the winner? Good luck. You're slowing down. Who's it going to be? It is Dylan. Dylan Ashiani, well done. You are the winner. Obviously, you've already signed up, so don't worry. We will find you and we will send you an email with you winning our paper 2 boot camps and paper 2 cram classes access for free. Well done. If you don't, guys, it's only £10 per class. As you can see, all the content we're trying to cover, we're really doing everything we can to give you full access to everything, all the notes you need, all the information you need for that. So thank you very much. One last thing, guys, before you go, if you could be so kind, there is one thing I would like to ask of you. Please, could you drop us a review? I'm just about to send the link in the chat here. We'd love for your feedback, hopefully positive, and that you enjoyed it, just so that others are aware, and we encourage more people to join, make it even better. The more we do, the bigger we are, the more people are aware we do quizzes, the more chance you have of winning bigger prizes. It allows us to do more with it, allows us to get more people involved, allows us to accelerate things we're trying to do, more content, more A-levels, things like that. All of that is helping by having more of you with us. So thank you very much, guys. You're going to give 5 stars. Thank you very much. Really appreciate that. Minto Play, will I get P2 Bootcamp as well? I mean, if you're Dylan, then yes, that's you. You'll get paper 2 of the boot camps. If you're not, then like I said, I gave you the link at the start. Jones dropped it earlier in the chat as well. If you can go to our website, and you will see you can find access to signing up for our paper 2 classes, just £10 per class. See which ones you're going to sign up for. Or if you want to join us for everything, the boot camps as well as the cram classes, our FRL classes package is just £22 a month. So for this next month, you'll get all the boot camps, all the cram classes coming up, and we have some FRL classes in between when Ian and I go through the remaining topics in more detail. And then we're going to do some paper classes as well. We're going to go through a paper, run through it as well as a class. So giving you that exam technique practice as well. Cool. So I'm going to answer a few more questions, guys. Anyone want to go through anything? I'll explain it over the next 5-10 minutes or so. Excuse me. So how did you not win? Sorry. It's unlucky. It's a lot of people there. It's a small chance, but unlucky. The group tuition, no, I don't do that. That's separate. So that's with Neen. As much papers as possible for revision is good. Differences between nuclear and fuel reactor. So what do you mean by fuel reactor? Do you mean like a fission fuel reactor, like fossil fuels? Excuse me. Yes. So the difference is how the energy is created, right? So the energy in a nuclear reactor is through nuclear fission. That releases your thermal energy. It then heats up water in air, and that turns it into steam. The steam turns a turbine and turns a generator to produce electricity. Fossil fuels, the fossil fuel is burnt, so the coal, oil, or gas is burnt. That's where your thermal energy comes from. Everything else is the same. It heats water, turns into steam turns a turbine generates electricity. Exactly the same. Yeah, the only difference is a nuclear reactor uses fission to generate energy. Fossil fuels, fuel reactor uses fossil fuels by burning them to give you energy. 5 stars, guys. Honestly, thank you very much. Thanks so much for that. It means the world. Really appreciate that. I'm glad that you got use out of it. Obviously, you have all these questions to try. Like I said, we're going to work on some marks. Hopefully, we can get them sent out to you as well. Those of you that are joining us for the other paper 1s, look forward to seeing you there. I'll be keeping an eye out, and Neen will be covering those. And otherwise, I'll see you hopefully for the paper 2s. Take a look on our website if you're not signed up already. We'd really love to have you there as well. Paper 2 is always the more difficult one, guys. Yeah, so that is the one where we're trying to help people the most. More difficult topics in physics, especially magnetism. Very difficult topic. Waves, a big and quite difficult topic. So hopefully we can help you. Does a split ring commutator reverse the polarity of the current? It does change its direction every half turn. And that is something obviously we'll go into more detail on in paper 2. Obviously you're in FRL classes, Dennis, so you know we'll be covering that. When we get the mark schemes, we're working on those. We'll try and get those to you in the next couple of days, hopefully. So watch this space. It'll be on probably by email to you all. Any predictions? We don't do predictions, which is why we just want to give you all the content. It's not safe to do predictions because what if you think of something and then something else comes up in the exam? Just learn all the content, try as many questions on every topic as you can. Then it doesn't matter what comes up, what is predicted, you're going to have covered everything. Yeah, it's the best way to revise. Paper 2 is hard, exactly. Yeah, forces can be hard. It's a massive topic. Waves is a massive topic, and so is magnetism. Yeah, it's only 3 topics, but they're much bigger. And for triple, you have space as well. Yeah, so difficult topics, more equations. So yeah, please do join us for paper 2 if you can. We want to do our best to help you on that as well. You get another revision guide, more questions to practice, just a full set of notes ready for revision. You can call it a displacement can, Ruby. You can instead of a Eureka can. Obviously, just because of its name, I would say preferably use a Eureka can, but you're not wrong saying a displacement can. What else? Is the displacement method for density the same as the phase method? Yes, it is. That's the same thing. That's what we're talking about, exactly. Life cycle of a star, that is going to be in paper 2. Yeah, so join us for paper 2. I'm not going to go through that now. And this was purely for paper 1, but we will cover it. It's a long life cycle, and that's for triple students as well. So it's separate for them. Was this paper emailed to you? Yes, if you signed up to join us for this class, even if you haven't right now, you can still join us and join and on our sign up page. And we'll send that as well one more time. You do get access to the workbooks if you joined us now. So here you go. I'll send the link here. Check it out. On there, you can see where you can sign up. And also, once you signed up, you can just sign up, obviously, for these paper 1s for free. You'll get access to these workbooks. Signing up for paying for the paper 2s, you'll get those as well. And that will give you a link to access the second paper as well. Yeah. Wicked. You found it in the email. Perfect. Good. Does radioactive contamination have to be on humans, or can it be on like sand? Yes, it can, but obviously the damage it does to sand isn't what it will do to us. Yeah, so it can, if it touches the sand, it's contaminated it, but it will more happen by irradiation, right? The sand isn't going to contact it. The irradiation will travel to the sand, let's say. Yeah, but we always talk about radiation and irradiation and contamination in terms of us as humans more than other objects. You didn't get the Gmail, don't worry. We haven't even finished the class yet. We will be sending it to you. So just keep an eye on your emails in the next day or so, and it'll be with you. If it doesn't in a few days, then contact us, but it will be with you soon. Yeah, we'll be working on that behind the scenes, but I haven't finished the stream yet, so it'll be something we'll do in a bit. Cool. Thank you very much. Thanks, Sammy. Much appreciated. I'll see you in physics paper 2 class, boot camp, sorry. Look forward to seeing you there. Thank you very much, guys. Like Jonas dropped in, if you have any issues or concerns around boot camps, cram classes, any questions you have or your parents might have, drop it at help@flashrevisionlab.com, and we will answer those questions and help you out. Okay. It's been a pleasure. Enjoy the rest of your Sundays. Have a bit of time to wind down. And yeah, look forward to our rest of our revision sessions coming soon. Thank you very much, guys. Take care, and I'll see you soon. Thank you very much. Thank you, guys. Take care. Good to see you. Look forward to seeing you in the other classes as well. Recommend it to other people. Anyone you know that would be interested, send them this link. Thank you very much, and see you in the next session. Yeah, we're going to smash this. Not long left. Just over a month and a bit of revision. You'll be in your exams, and then it'll be summer holidays in no time. So look forward to it. Keep smashing it, guys. Take care.